We were just talking a little bit about packet radio and packet satellite. You mentioned the gateway notion. This is a point where we come to Yogi Berra's fork in the road, which we're going to try to take,
let's
right?
Take it, yeah.
There are two ways to do this. You have a long history at DARPA. You were there for 13 years, and you did a lot of things in addition to the things we've talked about so far. What I'd like to suggest is that we stay on this track, continue talking about the open networking ideas, which I think you actually were working on before you got to DARPA, and then go talk a little bit about how all that evolved into internet, and then come back to look at some of the other programs that you were involved in while you were at DARPA, so as to try to keep this thread more coherent. So you mentioned just briefly this open architecture idea. Was that something you brought to ARPA, or is it something that evolved after you got there?
Well, it must have been in my head, but I don't recall consciously working on that before I got to DARPA. What I had been working on at BB&N was the notion that we really needed a different kind of protocol in the host computers than the original NCP one that you and Steve Crocker and others worked on. That protocol, for a variety of reasons, ended up being more like what I would call a protocol that could deal with a device like a line printer, where if stuff didn't get properly conveyed to that device, you'd press the reset button and redo it. I mean, you wouldn't expect radio signals to jam the printer. You wouldn't expect lost packets to show up on that interface, and so forth. And the model of the ARPANET was a very reliable communications device that would just convey things, and so the device at the other end was sort of just like a line printer. And I knew that, in the world of the future, we needed to look for something else. We might have radio links, we might have all kinds of other things. I was not thinking of multiple networks, but that we needed a protocol in the machines that would behave more like a communications protocol. And I actually wrote a paper on that subject. It was called something like Communication Principles for Operating Systems, that Bob Metcalf cited in his thesis. And it was a start down that path. So that's really what I brought to DARPA, along with a lot of expertise in building networks. Mm-hmm. When I began to work on creating these other networks at DARPA, that's when the notion that we needed a way to make them all work together showed up. That's where the open architecture notions came from. And I think it's fair to say that I had a pretty good notion architecturally of what this should look like, at a fairly good level of specificity, without working out the details. Of course, you and I probably, in a way that neither of us could have done all by themselves, really worked that out in a lot more detail at the specification level. But, I mean, the idea that you would have gateways between these nets that could handle the protocol translations, that could deal with all the impedance matching of error messages and whatever, it's all part of what I was looking at the time. And the question was, how do we go from some very general idea like that to something specific that could deal with this? I knew we had to address the devices in a more general way, because the ARPANET lets you address wires on it. So if you had something on a net 3 away, how were you going to specify what that was? So I figured things would have unique identifiers, but I didn't know what they would be at the time. And I started working with Vint Cerf, party in the first part, and together we ended up detailing that. Vint brought detailed knowledge of protocols to the table. He actually came out of the computer science side of the world. That's a part of the world that I hadn't come out of. I came out of the communication side. So we brought different things to the table, but it was a collaboration like no other one that I've ever had in my career, because it just clicked. I mean, we often, just saw eye to eye on everything, and every now and then we wouldn't. And, once that would happen, we'd have this, heated debate, and we'd sort of pretty soon come to the conclusion that the problem was just we had different assumptions about something or other. In later years, when we were working together, when that would occur, one or the other of us would sort of say, okay, wait, let's stop, let's go back to our assumptions, figure out what it is, because if we're disagreeing on this, it's probably in an assumption, not the reality, I was saying, here's what we need to do, and I'm thinking 5 years from now, and Vint's thinking I got to do it in the next 2 weeks, and how, so how's this going to work? And so between the two of us, we sorted that out. I mean, we could try and see if there are any items that were of fundamental disagreement on the technical level, but I'm not able to stipulate any right now that didn't have any genesis in different assumptions that were brought to the table. So together we were able to work out the nature of what this architecture would look like in fairly detailed form, and we wrote it over. We had a lot of meetings on the subject, both at DARPA and at Stanford on the West Coast. And at one point, we then decided we got to get this down on paper. And we got a conference room in the old Cabana Hyatt, which was on El Camino Real, right opposite the old Ricky's Hyatt, which I guess is
south of Stanford University. Yeah,
which I guess neither of them are there, although the Cabana building may be there with a different name. And it was one of the conference rooms on the first floor, you know, the name like the Lanai Room or something like that. I can't remember exactly. And we sat down to just write it, and we wrote it over the course of, I think it was a weekend. And I remember that so vividly because we pretty much had in our heads what this was. It's just a matter of getting it on paper. And I remember saying to Vint at the time, "You want to start or shall I?" And he said, "No, I'll be happy to." And he took a pencil and a pad, because that's all we had at the time, no laptops. And he sat there for all of about 4 or 5 minutes, and nothing was happening. Not a word was going down on the pad, nothing. And I finally said, "How you doing?" He said, "Well," he said, "I don't know where to start." You know, the space was so large. So I said, "Fine, why don't you give me the pencil?" And so I started to write it out, and I wrote, and it's not that he didn't have it in his head, he just wasn't sure where to start, I guess. And so I wrote out the first 8 or 9 pages, then he said, "Okay, give it back to me." And so he took it and he wrote the next 20 or 30 pages, and then we went back and edited and reiterated, and that's what produced that very first draft, which I wish he had kept a physical copy of, because it's probably worth its weight in.
We had my secretary at the time, Carolyn Tyne, typed the thing up, and I thought after she typed it there was no reason to keep the written version, so we threw it away.
So she threw it away.
There's a life lesson hiding in here of sorts, or at least a practical one, because Bob's style of writing things is to sit down and just start writing. And it doesn't matter, you know, in what order, or it doesn't matter. The point is getting the content down on paper.
Getting out of your head. Yeah.
And out of your head. And I was trying at the time to figure out how the whole thing was going to look, and then start writing at the beginning, the proper beginning. And so I was stuck because everything depended on everything else, and I couldn't figure out where to start. So I've learned that lesson, although I don't exercise it as well as Bob does, is when you have to write a paper, just start writing. It doesn't matter, because you can go back and edit, especially thanks to computers. So
well,
thank you.
I learned to correlate that from Vint Cerf, which he probably doesn't remember right now, but when you're trying to make something happen, the first step is just do something. And Vint, at one time, had a big sign, you know, over his door that said, "Do something," you know, just do something. And that's sort of the implementation equivalent.
Actually, the origin of the do something, we're jumping forward in time here, because the person that told me that was Josh Lederberg, who's on the board of CNRI, and we were talking about digital libraries, and I was, you know, sort of describing all the things that could be done, and Josh stopped me sort of partway through all this, and he looked at me and he said, "Do something." I thought that was pretty good advice coming from a Nobel Prize winner. We will come back to CNRI later on. I want to try to figure out what to do here. We've got this paper. By this time it's September of 1973, and there's an opportunity to present the ideas before what was called the International Network Working Group.
Which was meeting in Sussex, England. And
exactly.
Late in September, or sometime in September of that year. So I go over there. Vint arrives a few days late with the box of the papers that his secretary has now managed to type up, minus the originals. And we present the material at this working group meeting. The reaction of the people there was, I think, muted relative to what it should have been at the time. I mean, people often ask, what was the press reaction to the first installation of the IMP at UCLA? And we said, well, it was a non-event. It was on the shipping dock, and the engineer brought it in, and it wasn't written up in the press. It was not like, Lindbergh's first flight to Paris. Nothing happened. Well, nothing much happened at this meeting either. We gave the presentation. People said, yeah, very nice, and that was sort of it. We went back later, revised the paper in cosmetic ways mainly, so it would be suitable for publication, and the IEEE Transactions on Communication published it in May of 1974. We were later told, to our great surprise, that it's one of the more valued historical papers. It was very interesting, but you have to have the original journal, which I do.
Oh boy, well I don't anymore.
But you were a member of IEEE at the time.
It's now worth at least $7,500 according to one of the antiquarian bookstores in New York, who's offering one of theirs for sale for that amount of money.
Except mine has my name on it with the mailing label.
Holy smoke.
So that's like having a...
Wow, you're right. That would make it even more valuable. So. Yes. Well, if your retirement plan doesn't work out, that might be the beginning of something new.
Yeah, I think I'll just keep it.
So we're at the point now where we've got this this paper published. The work continues at Stanford.
And UCL. And
actually not, because my recollection, maybe you have a different one, is that the specification, detailed specification before we could write code, took most of 1974, and I thought that we didn't engage BB&N and the University College London until we had the full TCP spec, which didn't come until December. So that would have been my rendering of the milestones.
So one would have to go back to the record, and I don't know exactly where that would be located, maybe in the archives. But BB&N was actually working on two separate things on the internet side at that point in time. One was the TCP IP spec, which was more dependent on the work that Vint and company were doing. But they were also building parts of the packet radio system. And the packet radio system was controlled by a mini computer that had a station, and that station actually had embedded within it an interface to the ARPANET. So in some sense, they were going down the path of building gateways before we had the full TCP IP spec. And there never was a full spec for a gateway written. Nobody ever wrote a document that said in detail, this is how you implement a gateway. All we did was specify what the functionality of the gateway had to be. And some of the work on the IP addresses really didn't come until later either. So.
Actually, I think that either you've discounted a particular document or you didn't remember it, but Virginia Strassazar at BB&N wrote a document, IEN 30, called How to Build a Gateway. So this was BB&N's prescription for what you had to put into the gateway in order to make it work.
I know, but that was what BB&N was saying about how they would do it, and that's during the whole period while they were already working on the gateway stuff. I'm just saying that when I said that BB&N was working on it, they were working on that in parallel with the work that was going on the TCP/IP side of the world.
That document came out. This one we could check. I'm pretty sure that document came out after the TCP specs had been done, because it was all about encapsulation. The station, which had the interface to the ARPANET in it, eventually became the gateway between ARPANET and Packet Radio Net. But a lot of those things didn't get tested until
77.
That's
right. No, when I said they were working on it, I don't mean they were necessarily implementing it in the form that you were talking about. But as part of their work, that was one of the things they were supposed to be thinking about.
They had to, because the only way they could, the packet radio system was being implemented at SRI, right?
They were doing the integration and field testing.
Right.
The radios were being built by Collins Radio in the Dallas area, and the control part of it was the station, which was a PDP-11 mini computer, and BB&N was building that one.
And it was Jerry Birchfield's group that was doing the station.
Jerry, Ginny was part of that, a number of others.
So we did some tests, if I remember right, of packets flowing between the packet radio net at SRI and ARPANET somewhere in the 75 or 76 time frame, before we had implementations of the full TCP/IP. Anyway, my recollection is that we didn't start seeing code coming out of BBNN for TCP until sometime in '75.
Oh, I'm sure that's true. But was there some part of what I said that you were having trouble with? Because I don't think what I said is challenged by. I think that's exactly in agreement with what I said.
Yeah,
before.
no. The question was, when did UCL and BBNN start working on internet? And my recollection is that they didn't start until the '74 TCP spec
on the
was done.
TCP IPs, the TCP stuff. But when I was talking about the BBN stuff, it was on the gateway stuff. And if
That was on the packet radio program.
If I threw UCL in the mix, I probably should not have. They were not at that time.
So we've got this time period now from 74, 75 through 78, when this protocol starts getting more and more refined and everything else. And in that same period of time, I leave Stanford and come to ARPA. So
sometime in 1976, as I recall.
Right. Yes, in August or something like that. So what I'm curious about is how we characterize your involvement in internet as this all unfolds, because for a while you get to focus on a lot of other programs at DARPA, because I'm at ARPA helping. But then I left in 1982, and
well, between 1972 when I came and 1976 when you arrived, I was basically running every one of those programs, with the exception of the ARPANET program, which was run by other people. So we had efforts to build, end-to-end security devices that I started. We had programs to work on sending packetized speech, because they're the precursor to VoIP technology today. Remember, we were sending, packetized speech through a 50 kilobit network, and one conversation in principle could have been, I suppose, 64 kilobits per second. It's hard to get all those bits through. So we actually were demonstrating how to do it, and later we, using compressed speech techniques, using LPC, CVSD, and other techniques, we're actually able to send full-blown conversations through the old ARPANET. It required changes in certain protocols because we couldn't acknowledge every packet because you needed to maintain continuity. But we did that. So there were a lot of programs that I was running: the packet radio program, the satellite program, the security program, the command and control program, all of that stuff. When you showed up in '76, by that time I think I was chief scientist and probably deputy director.
You were
of the
deputy
office.
director at that point.
And I was more than delighted to see you show up, because we suddenly had somebody else who was capable of providing vision and leadership for that. And we worked together on that pretty closely for the next 6 years. I would say that the most significant thing that we did during that time frame was to set up the initial things that became the Internet Standards process going forward. And that's a very interesting issue, because Vint and I had many discussions about what would happen if one or the other of us were hit by a bus or the equivalent. I was more concerned about him because I knew what I would do, namely have to take it all over again, and I really couldn't. I didn't have the time and couldn't afford to. And so I implored him to set up a kitchen cabinet of some sort to help with the management of the program, mainly so people in the community would know about what's going on. He kind of resisted that notion as a notion, but then he came up with the equivalent with a different context. He said, why don't we set up a group to help us configure the internet? People are going to have to know how to deal with that. And he called it the Internet Configuration Control Board, which got populated with roughly a dozen implementers from around the country, mainly people he knew well and that he'd been working with. And I think we got Dave Clark from MIT to chair it. And that became the sounding board for what we did. It didn't have any real responsibilities at that point, but it did have a lot of knowledgeable people who were in very close contact with us. We were still making the decisions at DARPA, but it was a start of something of significant proportions later on. In 1982, when Vint left to go to MCI for the first time, I took over the program again and started to run it. During that period, we had brought in another gentleman who's now deceased, Barry Liner, and Barry took over part of the packet radio program. He had been introduced to a lot of these programs during that period of time, but he really didn't know much about the internet at that point. So I took it over and ran it for another year and tried to get Barry to become more involved in the internet so he could pick it up. And his approach to things was very different from Vint's, whereas Vint could literally pick up anything and engineer it on a moment's notice and do a good job, because he was an engineer and he was an implementer, and as well as a pretty good manager of others, but he was good at doing it himself as well. Barry was not of that ilk. Barry was a good process guy. Barry had a lot of technical expertise. But he wasn't about to make decisions about this, because it was a big system that by 1982 had already become pretty complex. So he was more comfortable relying on another group to come back with the recommendations. Or I suppose he would have taken them from me, although I didn't interfere too much at that point. And so I introduced him to the ICCB, now that Vint had gone, and he became uncomfortable with that whole mechanism. And the reason was, when Vint had started it, it was like 12 people and a few what I call strap hangers, people who just wanted to sit around and listen. But by 1982, because that was where almost all the really interesting discussion was happening, that was happening anywhere outside of DARPA or in the community in a collective way, people just wanted to sit in and listen. And I don't know the exact number, but there were several hundred people that typically we had to invite into these meetings. So you couldn't have a meeting of 12 by getting a small conference room. You had to have an amphitheater, theater in the round kind of style, in order to have a meeting of just this set of 12 people. And Barry looked at it and said, no, and he and Dave Clark got together and they decided that they would like to recommend a restructuring of it. Namely, we get rid of the ICCB, create another body, which they call the Internet Activities Board, which essentially had the same people, plus or minus a few, and to take all of the discussions that were going on in that group that people wanted to listen to and put them into a series of task forces underneath. And there were 10 of them initially. One dealt with autonomous systems, end-to-end routing, privacy, security. There was one of those task forces whose job it was to maintain the punch list, because Vint was gone by now, and the internet was sort of being born from the introduction of the TCP/IP protocol. So what we needed to do was get all the hosts on the net sort of aligned. So this other group had the responsibility for the so-called punch list. If you've ever bought a house, you know that before you take possession, you want to make sure the water works in this, and the switch is okay there, and the plug is installed here, and the leak is fixed. They're the details. That's what's the punch list. And so this group, which was at that point chaired by Ed Kahn from DCA, was in charge of the punch list. And the other 10 working groups could do whatever they want, wherever they wanted, and it didn't have to all be in one place, and they could meet asynchronously in different places. And so that was the formation of what's become the current standards model for the internet. This was an early form of it, but it had the right shape and form, and it grew over time. So from 10 initial groups, a few years later it was up to 50, and suddenly the ability of the IAB, this 12-member group, to manage all of them, because they were chartering the groups and they were overseeing them, just became too large. And the responsibility was then given to this other task force, the Internet Engineering Task Force, which had pretty much prosecuted its punch list to manage the other working groups. And it was another one set up to deal with research, but that was the beginning of the structure of the modern standards process that's been used to manage the internet. That sort of took hold and started to grow. In 1986, after I had left DARPA, Vint had also left DARPA a few years earlier, and Barry was leaving at the same time. DARPA made the decision to get out of networking. Normally they go into an area they funded for a while, then they move on to the next thing. Well, in this particular case, they decided it's time to let it go. NSF was very interested in taking it over. Eric Bloch had recently joined as the head of NSF, and he wanted NSF to get into networking, to broaden it out into the science and education community more broadly. And they did. And I think one of the seminal decisions that NSF made, and I attribute it to Steve Wolf, but I'm not sure who else was involved, was to build upon what DARPA had done with the TCP/IP protocols.
Actually, Dennis Jennings takes the credit for having made the original decision to move to TCP/IP, and he wasn't in the networking group, I don't think.
There was the supercomputer side.
Supercomputing thing. But Dennis was on leave from University of Ireland, and claims that that was his responsibility.
So let me roll back a bit then,
Okay.
if you really want to go through that.
We also need, by the way, to roll back to 1983 because we skipped an important milestone that we should talk about.
I'll get back there in a
Okay.
moment, but I want to point out that the National Science Foundation had gotten really interested in networking by the late 70s. They had a few aborted attempts to do something, but they were really serious about wanting to do something. And they had a meeting at the University of Wisconsin that I attended, and out of that came the basis of a project called the CSNet project, which was really an effort that allowed the research community to get on a commercial net, which in this case was Telenet. We worked the interconnection between Telenet and the ARPANET and worked out all the arrangements with NSF to allow that. Vint was the chief technical liaison to NSF on that, helped with the engineering of it, and I handled the political administrative agreements to enable that to happen. By 1983 or so, NSF had made a decision that they wanted to work more closely with ARPA on supercomputers, and we actually had an agreement with them to support that. It didn't actually go as planned because they wanted something to happen instantly, and this was at a period where DoD was growing the defense version of it, and the net result was that while they made a decision to go with TCP/IP, it was because they were going to build on top of the ARPANET using these new protocols. The eventual decision of NSF was to build their own network called the NSFNet, and that's where Steve Wolf essentially decided to build upon stuff. So NSF had some incremental decisions along the way to do that, and there were many other structures and bodies, networking councils, and the like that had gotten set up along the way, but that was sort of what happened on the NSF side. So I think they did, great credit to the science and engineering community, the research community in general, but I think they also did their decisions made it possible for the work that we did to become widespread and well known. So I guess if we now roll back the clock a bit, 1983 was the time that we actually converted the protocols on the ARPANET from NCP to TCP/IP. The plan for doing this had been worked out a number of years in advance. Vint, I think, had been working with John Postel, and John had actually written down the plan for what the transition would look like, and we announced it to the community. DARPA did, probably at least a year or two before the transition date.
Like mid-'81 or thereabouts, we told everybody that by January 1 of '83 we were going to convert over. Incidentally, Dan Lynch had a role to play in this too, also at ISI.
So, but by the time the transition came about, Vint, of course, had now gone. He was at MCI, and so it fell on me to manage the transition from the one protocol to the other, which was actually instructive in many ways because it didn't go at all like I expected. I mean, here we had a plan for what was supposed to happen, but it didn't quite happen that way. And, we kept citing, dates and asked people, are they ready? But even a week before the transition, we were getting requests from many people to delay it, Are you really serious about doing this transition in a week? And we're not ready yet, Well, you've had a year or two to get ready. Why not? Well, we didn't think you were serious. I mean, and so we then had to figure out what's the strategy for not breaking the net, because not everybody is going to be able to make the transition. And we actually ran both protocols in parallel for a period of at least 6 months until finally we were able to just sort of shut down the old. And the ARPANET then ran with the with the TCP/IP protocols, until it was decommissioned sometime in the 1990. And I think it was actually in 1990 that the last node was decommissioned. And by that time, NSFnet had taken over as the backbone, along with a lot of other networks and commercial nets that were now beginning to become part of the picture, although they weren't officially allowed to connect to the NSF or any of the government nets. That didn't occur for another 3 years until a bill passed that was sponsored by Rick Boucher, a House member from Virginia, was actually passed in early 1993 that enabled NSF to open up the NSFnet to commercial traffic.
Actually, this is maybe a place where we don't have the same recollection, because now we're getting all tangled up in CNRI stuff. Maybe we'll have to come back to this, but I thought that by 1989, when we brought up the MCI mail internet connection, that same year there were 3 commercial networks, and I thought they were allowed to interconnect with NSFnet.
There was an agreement to allow electronic mail interchange. In fact, it was pioneered with the MCI mail, and the discussions that you had with the FNC was what enabled that, or maybe it was still the FRIC at that time, the predecessor to the Federal Networking Council. And soon thereafter, very soon thereafter, AT&T and Sprint were allowed to do email. There were federated commercial nets through something called the Commercial Internet Exchange, the CIX, that had been set up. And there were a number of NSF-supported nets that were becoming murky participants. For example, there was a network that was set up under NSF aegis in New York with support from New York State and NYNEX called the NYSERNet. And one of the participants in that activity was a fellow named Bill Schrader. And Bill had essentially left. I think he was president of NYSERNet. He had left to set up a separate organization called Performance Systems International, which later became PSINet. And he took the people and he took the technology, so there was really no issue about whether they would continue with them or not. I remember having breakfast with Cass Skripczak, who was the chief technology guy for NYNEX at the time. He hadn't heard about it. We were at a governor's meeting in New York at the time. And they ended up deciding to support it because they weren't trying to ruffle feathers, but I don't think they were very happy about what happened. But the bottom line was that the PSINet activity, which had a lot of the research community on it, was now instantly a commercial net. And so suddenly you had the interface to the NSFnet, and you had both allowable and unallowable traffic and no way to sort it out. So even though there was a policy that defined what the use was, the reality was there was no visibility into what was actually happening. So you're right about, sort of what was going on. It was a rather gray and murky area, but the bill that made it all legal was the voucher bill. I think it was put forth in late 1992. I think it was formally passed in early 1993, and it gave NSF the congressional imprimatur to open up the NSFnet to commercial use.
They had an appropriate use policy at NSF that would have officially restricted the commercial traffic to flow only on the commercial systems, but as Bob points out, things were so interconnected that you couldn't tell, and there wasn't any good way to mark the packets as this is a commercial packet and this isn't.
Right.
Well, let's, unless you want to continue on the internet path, I was going to suggest to go back now to talk about what happens, particularly you get Barry Leiner comes in 1983.
Barry Leiner comes into the program. He actually joined DARPA in 1980.
In 1980?
I believe, yeah. Or maybe 81.
So Barry, or you're saying Barry and I overlapped more than I thought.
You guys overlapped at least a year.
Yeah, that would be 81 to 82 or
could have been 81.
I remember fairly low overlap. He was working, and we knew about him because of the packet radio program, because he was working on detectability of the signals in the packet radio net. But in any case,
we can get the exact numbers if you like. But it was, you guys overlapped for a while.
Yes. That's absolutely true, because there had to be some kind of a handoff. The thing I wanted to come back to, though, was the other activities that occupied your time at DARPA. You've already mentioned the packet radio and satellite packet speech and security in the general command and control program. But it seems to me that one of the most impactful programs was the VLSI program, because it had such an influence on the number of people who knew how to program or how to design VLSI chips, and also the strategic computing program. So I thought maybe you should tell us a little bit more about those.
The 1970s were a very turbulent time at DARPA. We were fighting the Vietnam War. There was a presidential resignation. There was a lot of alienation in the research community. DARPA saw the loss of many of its key researchers. Some were for commercial opportunities. Some went to Xerox PARC, some went elsewhere. But the overall budget that was available for research in information technology, which is really what we had responsibility for, had dropped precipitously between the period of roughly 1973, 4, and maybe 78, 79. So during that period, I would bet more than 2/3 of the funding, and maybe 3/4, actually disappeared as research funding. That the budget didn't go down by that much, but a lot of it was shifted off into command and control experiments and other things that the research community wouldn't have viewed as research. They weren't necessarily inappropriate things to invest in, but the research program itself was being very badly gutted at the time. And my concern was, and in fact, one of the interesting things is people have often asked me why I spent so much time at DARPA. My view was that this was the best hope for the research community at that time. And if we walked away from it and let it go, that in the final analysis, everybody would regret it. And so my view was to try and build it back up again, do what I could. And fortunately, I had the support of the director at that time. When I became the deputy director, the head of ARPA was a fellow named George Hallmeyer, who was a graduate student along with me at Princeton, so I knew him well. And I would say he actually gave me a tremendous amount of support while I was there, and enabled me to do a lot of the things that I did, with his backing. He got replaced by a gentleman named Bob Fossum, who I also got to know very well and had great respect for, and he also gave me, tremendous support. And of course, the program then, we managed to grow it significantly under Bob Cooper when he was there, but he had a much more defined mission and focus, which, I could really appreciate, and Bob and I actually ended up working together to grow that program significantly. But the first thing that I did was, in figuring out what to do to at least repair the damage, get back to where we were before, was to create a program in VLSI design inside of DARPA. And what I did was to build on some work that Carver Mead had been doing for many years in trying to characterize VLSI foundries. And he had come up with a standard way of describing designs that could run on multiple foundries. So it allowed you to break the barrier of having to know proprietary design rules, which made it impossible to teach in the classrooms. And even if you could teach it in the classrooms, there's only one foundry that can implement it. So you weren't able to really do justice to the field. In the middle 1970s, it was also clear that computer science needed to deal with computer architecture issues as part of their lifeblood. And that without some ability to do VLSI design, that field would suffer pretty dramatically. So we were also moving into a range where it became clear that submicron VLSI design capabilities were about to show up. Carver Mead wrote a wonderful paper, I think, with Ivan Sutherland and Com Everhart, that had a big impact on me in terms of just sort of laying out the semiconductor part of the field. And so I knew that designing devices that had submicron dimensions would be very difficult to do by hand. I mean, it's one thing to design a chip that might have 100 elements on it. It's another thing to design a chip that might have 1 billion elements on it. You really need computing help, and therefore it was an appropriate thing for the information technology part of the world to deal with rather than just the material sciences part. So I managed to get support for a new program in VLSI design, and we built upon what Carver had done. Carver and Lynn Conway got together and wrote a textbook on the subject called An Introduction to VLSI Communications or Design, I forget the title, that was used in a lot of classrooms. We provided support for a lot of the universities to make available money for research in that area, and we provided a fabrication design service to do that. Xerox PARC actually prototyped it with Lynn's help, but Xerox, I do not believe, wanted to continue to support that. It wasn't part of their long-term business interest or strategy, so they actually approached me, some of the key people there, and asked if we could help. And Lynn was, I think, part of that process. And I ended up moving it to the University of Southern California. Under Keith Unkefer's aegis, Danny Cohn became the initial program manager for that, and they named it MOSIS, which MOSIS stood for MOS Implementation System. And my one contribution to that was to introduce the I. Danny wanted to call it MOSES, and I thought that sounded just a little too
biblical.
Biblical, yeah. So that's how MOSIS got created at ISI. And they've continued to run it to this day in support of the entire research community. So that was one of the things we did. The research community got to use it, and it made it possible for people to teach VLSI design in classrooms, to get students to be able to implement it and to do really quick turnaround, low-cost designs, and it turned out to be a big win.
I was going to suggest that there's an interesting analogy between what was done in the VLSI program and what was done in the Internet program in the conceptual sense. In the VLSI program, as I remember it, you were trying to have people design circuits that were fabrication independent, so that the primary parameters had to do with line width and didn't have to do with specific physics of particular fab lines. So the idea was to be able to design circuits that could be implemented in multiple fabs. And it occurred to me that there's an interesting analogy to the Internet, because we intended that the packets be carried over arbitrary communication systems, that we were insensitive to which kind of communication or transmission system was in use. And so there's an odd parallel there that hadn't occurred to me until you started talking about the VLSI program.
It's a valid parallel. I mean, there are some things that are obviously different and some things that are the same, but the big problem was that at that time that the fab sites all had proprietary design rules. And it wasn't so much that we were trying to do fabless ones. I would have been perfectly happy if every one of the fab sites had said you could make the proprietary design rules publicly available. Then you would end up with something, at least you could teach it in the classroom and they could publish papers on it and say what they did. But it had the added advantage that if you could have ones that would run across a multiple set of process lines, you would have much more powerful design methodology. Now, Carver was the one who came up with the original design methodology. I think Lynn helped with the exposition of it, and I don't know exactly what role they played because they worked together pretty closely. She's a very good writer, very good explainer, and it really made that textbook come alive. But I can't believe he checked every single line, every place in the whole world. So it's very likely that whatever designs he had a good chance of working. Maybe in fact did work at all, but we didn't know that and he didn't know that, because he could only say of the 10 that I know about in detail, I think this will work on all 10 of them. And so those are what we used, and we had a small set of fab sites that we were dealing with, and these designs worked across all of them.
It seems to me that this is an example of the power of abstraction in some respects. I mean, by getting things at the right level of abstraction, you can generalize a lot more readily than you could otherwise.
Well, given that you're raising that issue, I want to say that one of the difficulties with deciding what to do and what level of abstraction to use had to do with saying with specificity what it was you wanted fabricated. You can imagine at one level, the designer could have said, I want a chip that, solves the DNA sequencing problem. And then it's left to the designer on the other side who knows about silicon and the physics to figure out how to do that. He's got to solve the whole problem himself. You get down one level and the designer could say, well, I want a chip, but here's the block diagram of it, and it's got a modulator here and a detector here and a rectifier there. The designer sort of has a clue as to what you want, but he's still got to do the work. And as you go to lower and lower levels, you could have somebody provide a circuit design and say, go implement the circuit. It doesn't say where on the chip the resistors and transistors and stuff go, but he's sort of spelling out in some detail exactly what kind of thing he wants implemented. A level down, you could imagine a gate diagram. Here, where I want the gates to go, not the Bill Gates, but the transistor gates.
The T gates.
And one level down from that, you can imagine, a stick diagram, which literally sort of outlines where the base and the collectors of the individual transistors might go, or some higher level functional spec of a lower level design. What we ended up doing, and if you view this as kind of a parabola, at the very bottom of the parabola, there's a point where the two sort of merge, because every one of those other ones leaves enough room for ambiguity that something could happen that makes the design not exactly what you wanted. What I opted for in this program was to pick the bottom of the parabola, the very bottom. If you were to draw a horizontal line, figure out where it hits tangentially, it was a point. And that point was where the designer specified the artwork to go on the masks to do the fabrication. So there could be no ambiguity in the communication, and therefore we knew it would work, and it would be what the designer wanted, and the fab lines could build it.
Fascinating.
So it was a choice of specificity that's very low level. We have the same problem in the networking world, where some people might complain TCP/IP is sort of pretty rigid. It's got a lot of protocol parameters, but it'd be much better if you just had these two computers talk to each other in English. They could figure out what they want to do, right? But maybe that wouldn't work quite as well. What would they say about timing issues and fragmentation, and how would they figure out addresses? And but could that be done? Perhaps. Maybe the future will tell.
Well, of course, the big question is, will all implementations interwork? And that's the important part, at least for internet. There's another major program that you started while you were still at DARPA.
Oh, one other thing, Vint, just to
sorry.
close on this.
Yeah.
I was mentioning about Bob Noyce and the conversations. The reason he liked the DARPA VLSI program, because it was focusing on training individuals. That is, it was producing the human capital for the future of their industry, and it made a really big difference. I mean, there was controversy about it. Was it right to get university people trying to figure out how to do VLSI design or not? But if you focused on where the expertise was, not every one of them would be a world-class computer architect. Not every one of them would be a world-class physicist. But every one of them who came out of it would have the potential to learn at a later point in time. So he saw that as the big value, and I think that's been one of the main contributions. They've done some interesting things. I mean, the geometry engine that Jim Clark designed at Stanford became the basis for Silicon Graphics, and there are probably a half a dozen other major things that you could point to that made a big difference. But I think when all was put together, the biggest contribution was training people in that field and invigorating the computer science field in the process.
So I was about to shift into another program that you started sort of late in your time at DARPA, and that's the strategic computing program. So maybe you could tell us a little bit about the origins of that and what motivated it and what the outcomes were.
By 1992, we had pretty much gotten the funding level in IPTO back to about where it would have been.
You don't mean 92. You probably mean
72.
72,
72.
right. So,
Thank
okay,
you.
20 years later.
1972, no, I mean 1982.
82.
In 1982, we had pretty much gotten the funding levels in IPTO back to roughly where they would have been had the impact of the Vietnam War on research taken place. Not quite as high as it was, but within about 10%. So much of the anguish had now gone, and the question really was, where do we go from here? At any point in time, you're always looking for a rationale for the next thing. Well, if you trace the history of DARPA's investment in computer science, the motivation for starting that office in the first place was based on a vision that I guess was largely attributed to Licklider. Many other people may have had pieces of it, but it was a vision that talked about moving from batch computing to interactive computing, from moving from numerical computing to symbolic computing, moving from a localized environment to a networked environment, and much of that by the early 80s had come to pass. we no longer were buying, UNIVAC machines and the big mainframes. IBM still sold some, many of the companies still sold them, but for the most part, a whole new way of doing computing had arisen, both through mini computers and now with the microcomputer coming of age. So what was the vision for the next 10 or 20 years? That's what we were struggling with at the time. Also, we knew if there was a vision that the computer science community could benefit from it. We were looking for ways to get more money into R&D because the agenda of things that needed to be worked on was hardly fulfilled at that point in time. And also the Reagan defense buildup was happening. So we knew that there was opportunity. And so the program that I put together with a lot of help from Bob Cooper, in fact, in many ways the decision to push it was Bob's, but I ended up structuring the program, was strategic computing. And the whole goal there was sort of 3 or 4-fold. I mean, big items. Item number 1, let's figure out a way to have all this computing technology that we've been working on for the last 20 years at DARPA, and that's now starting to take hold, be made available to industry so that the DoD can make advantage of it. So goal number 1 was get it into DoD. The strategy was you need industry help because that's what the DoD has to rely on. Furthermore, with all of that buildup, we also recognized that we'd have to get some of the other offices at DARPA involved. Bob Cooper was very interested in funding some early applications. To be quite honest, I was somewhat skeptical of that from a technical point of view because to build the applications before the technology that it was depending on had been started on, much less created, didn't seem to make good technical sense. But I think Bob's motivation was different. It was more political and strategic. What he was worried about was if you didn't take the other offices and get them thinking about what you're doing at the time you're ready to really do something, they won't be ready for it. And number 2, the politics of taking all the money and building it up in one office versus sharing a little bit of the wealth of the other offices politically probably didn't work. I understand that much better now than I did at the time because I was arguing technically at the time that, didn't make technical sense, but it wasn't a technical issue. It was totally a political and strategic issue. So we got the program actually launched and going, and it was the first really large-scale program in computing that had ever been funded anywhere in the DoD. Which isn't to say that lots of money hadn't gone into computing-related stuff. I mean, I don't know when the B-1 bomber program started, but I'm sure there was a lot of computer stuff on that required a lot of coding by different contractors. But it was mainly, sort of contract software development for specific applications as opposed to opening up a whole brand new area and field and research. It was like $1 billion program that we got started. I was very pleased at that, and Bob and I went around to the research community at his instigation to sort of give him a heads up on it, and he kept telling them, one, what do you think about the program? Because we had framed the program in a way that essentially covered all the research interests that I thought the research community ought to care about, and they actually ratified that. There was no project that somebody might want to work on that couldn't be fit into some piece of this overall program. It was into architecture, it was into applications, it was into AI, it was into VLSI. I mean, it just sort of covered the waterfront. But he wasn't sure, but I think he got a lot of reinforcement from the field that said, yeah, structure of the program is fine. He also pointed out this is going to make a big change. Are you guys ready for it? And I think that might have been misinterpreted because I think they were thinking a lot more money for the universities and therefore it's going to change the nature of the way the universities are, but they were all sort of saying, yeah, we're ready. But what he really meant is that industry is now going to start to play a big role. And so I think that wasn't exactly what the community was thinking about and expecting, but it turned out to be a pretty good synergy. More money went into research. A lot of that money, I would say the preponderance of it went into funding industrial groups to build up capabilities in multiprocessor architectures and speech understanding systems and image processing work and and the like, real state-of-the-art applications. But what it did more importantly was it took the IPTO budget and it grew it by leaps and bounds. It went from mainly the 40 million-ish level to maybe the 90 million level with the addition of the VLSI and other growth that got built into the program, and that took it up from 90 million to roughly the 200 million level, if not a little higher. So it was a big push. And by the time I left, we were certainly one of the biggest offices, if not the biggest office at DARPA. Mainly the Strategic Defense Initiative had taken the laser stuff away. But when I started it, we were, I think, probably the smallest office, or one of the smallest. So it's a big change in DARPA at that point. But it also changed DARPA in a fundamental way, because suddenly now you had all the other offices getting interested. Today, if you went into DARPA and you were to ask them, what money are you putting into computing, what you will hear back is every office is doing some. Well, but the mission offices are focused on applying it to mission purposes, and the research offices have carved out generally some very specific goals. Like the information processing office has been working feverishly on large supercomputers and on learning technology, very specific missions. And that's typically what DARPA has done. It's formed its agenda and it's focused on it. Whereas at the same time, the National Science Foundation budget, this is now circa 2006, has also grown significantly, but their purview has basically been the research community. So they go out to the research community to find out what are the issues that that are appropriate to focus on. NSF doesn't ask the Defense Department what to work on, and DoD doesn't feel like its job is to go ask the universities what should it work on. They all have their own mission and their own constituency, their own set of problems, and that's sort of where we are today.
Just out of sheer curiosity, Bob, did the Strategic Computing Initiative have any impetus coming from what the Japanese call the fifth generation network, or fifth generation computing program? As I recall, a lot of visibility associated with that, but I don't know if it motivated any of the strategic.
That's a great question. I mean, when I took over the office, one of the things I was trying to push was more money into informational infrastructure kinds of things. And I wasn't getting much traction. I mean, I wanted to build a knowledge base for science and technology, and I wanted to work on a variety of things that really didn't happen. We were fortunate in getting the VLSI program going, but I was trying to do more back then, so it wasn't really going very, very, very effectively in getting more money. In fact, it was a big enough achievement to get where we were, to get sort of back to the norm. Somewhere along the line, the Japanese started their fifth generation program with a stated goal of overtaking the US and moving ahead. They put all their marbles on a language called Prolog, which you may remember from back then hasn't really made a mark on the external world to any great extent. They were going to look into, they were dealing with pattern information processing systems and fuzzy logic and stuff like that. There was a lot of concern that we needed to do something to not be overtaken by the Japanese. And the head of defense research was a gentleman named Dick DeLauer, who I think believed very strongly that we should be combating that. And that's my belief. I did not have the discussions with him. When Bob Cooper and I talked about this, he said, I don't want to worry about the Japanese. I want to worry about what's right for defense. And what we do should make a big difference for defense. And so all of the stated goals inside of DARPA, no matter what you thought might or might not be the matter of reality, was let's do something that makes a big difference for defense. So that was the internal DARPA view and position. Like many other dual-use technologies, you could have asked about the internet. Was the internet to create this worldwide global goal? Maybe some people had that in the back of their heads, but if you asked DARPA, they would have given you a different point of view. In fact, if you really go back to the early days of DARPA and looked at the requirements for getting DARPA programs going, it was almost always to identify a specific defense need, to find a person there who would be a partner with you, maybe get them to fund part of your work, work out a transition plan. Well, if you think about the internet as an example of a project, at the time we started it, the rest of the military didn't have any time-sharing computers. They had a few batch machines that were used for various missions like accounting, where interactions were not de rigueur. As a result of having no interactive machines, they had no interactive computer networks. And so imagine trying to sell somebody a program to link together the networks they don't have to the computers that they don't have. and a transition plan and funding. I mean, it was basically not an argument that had any traction. It didn't fit into the mold. Fortunately, we were able to pursue that in the guise of the packet radio program because it needed to connect to the, I mean, it was a very specific need. And so we were able to develop the early TCP IP protocol specs that way and get the initial implementations and sort of demonstrate it. And at that point, it got a life of its own. But, you know, it's a tough sell.
So I suggest.
Could I?
Yes. Okay, we're on. You were about to say something else about the strategic computing initiative.
Yeah, the one other thing about the strategic computing initiative, which is probably not understood that well by others, was the infrastructural component of that program. We had argued that in order to enable the research community to do a lot of their tasks, they needed high-performance workstations. So we managed to work both through a combination of different schedules and purchasing agreements, the ability to get a lot of workstations to the research community, because at that stage, I mean, there were very few. I mean, the IBM PC had just come out. It wasn't powerful enough to do much of what we're talking about. Apple wasn't on the horizon yet. So getting the hundreds of machines out into the research community to start to seed a community that could make use of this was an important thing that strategic computing enabled. Furthermore, it enabled the initial internet connections to happen in most of these places. It enabled, we gave the institutions money to buy the local area net connections, get the machines, get hookups. This was a time when some of the commercial stuff was, you know, if not fully commercial, a glint in the eye. I'm not sure when, for example, the early nets got formed, but there was an early California network that, interesting, was named SurfNet. Not I believe after you, the California Educational Research Federation.
Foundation, right.
Foundation. There was a CalNet of some sort. There were a variety of kind of research nets being formed all around, and people had to get connected to it, and they generally had fees associated with it. People had to pay for that. And so the program enabled all that. So a lot of the infrastructure for the early internet happened through strategic computing, which caused it to get funded and in place. And very few people realize that, but without that program, we would not have seen the uptake of the internet after January 1st of '83. It just, there wouldn't have been enough machines to use it. There wouldn't have been enough networks to connect to it. It would not have been properly seeded. So I think that's a little known aspect of it. The other thing was an adjunct of the VLSI program was the decision to fund the University of California at Berkeley to build a virtual memory version of the Unix system. Now, the motivations of that were twofold. One, AT&T had obviously developed Unix and was making it available through licensing arrangements through, I think, maybe Western Electric. The university could get, you know, licenses to use the existing Unix software, but they couldn't get virtual memory systems out of AT&T. And so we funded Bill Joy, who was then an employee at Berkeley, and who later became one of the founders, along with Andy Bechtolsheim, of Sun Microsystems, to actually build a virtual memory version of Unix. The motivation was, number one, for image processing. We had a very large image understanding program that was ongoing. This is before strategic computing. These image databases were large. The existing software just couldn't deal with it properly. But more importantly, the VLSI program also needed it. And a lot of these VLSI designs were really huge and went beyond the bounds of what the typical system could deal with. So we had also funded BB&N to build some of the early protocol, the TCP IP protocols for the Unix platform. And so the decision was made to have Berkeley put the BBN Unix software package on the Berkeley distribution tape. We just essentially told them, please do that, because we were funding both and they needed this protocol. And Bill Joy's reaction to that was posed a problem for us, because he was not comfortable putting somebody else's software on that, but his system didn't do it. So what he ended up doing was sort of, I presume, just looking through the code and re-implementing it into the guts of the Unix system, and parts in the kernel, and I don't know how he did the actual implementation. And he made it work efficiently in the local area network environment that he was working with. You know, previously, many people had looked at this. I mean, Dave Clark was one of the first to pioneer putting TCP/IP on, you know, local workstations and getting it to work in local area nets and making local nets work. But this was a very specific project. And so Bill Joy actually did that coding, and it worked fine in the Berkeley environment. But he made some efficiency optimizations at the time, like he took the checksums, instead of putting them in the back, he put them in the front. I don't know all the details, but the bottom line is his implementation, which worked fine in that environment, wasn't compatible with either the specs or whatever other people were doing, and it took a while to sort that out. My recollection was at least a year and maybe more, and John Postel was involved, and perhaps lots of others. But that development turned out to be extremely important, because it's one thing to go around to people and say, please download the TCP/IP code, and oh, by the way, please integrate it into your operating system, and oh, by the way, please integrate it into all your applications, which at the minimum was a job for a wizard and hard work, and you'd have to then do it for every other application. Whereas by getting it through a single package from a commercial vendor, you could go buy their workstation or their operating system, and it came packaged for free. So it became the carrier of that part of the technology base, a big difference. Now the gateway stuff, you still had to configure your own, get a piece of code from BBNN, get an interface from here, buy a, you know, LSI 11 from Digital, or however you're going to do it. But shortly thereafter, probably 1985 or 6, we saw a number of companies emerge that became powers in the whole network field, including certainly Cisco, which was a spin-off of Stanford. There were some companies up in the Boston area that worked closely with MIT.
Yep,
but
it would have been Proteon, was the one
specific.
that first came out, as I recall. And 3Com actually had, and Bridge Communications had some role to play here, although they were often operating below the level of IP. But eventually moved into, at least 3Com moved into gateway router technology too.
And then there was Wellfleet in the Boston area.
Wellfleet, well, I don't know whether they were doing the same thing. And, you know, Bob Metcalf, you know, related to me how unhappy he was, because Vint had managed to convince Bob to go build a TCP/IP package and sell it, and Bob had done that. But meanwhile, unbeknownst to Vint, Dwayne Adams, who was working for me, had gotten the Berkeley guys involved in it. I mean, it was the net effect of this whole effort. And suddenly, you know, Bob saw the investment that he made being undercut by this free package coming out of Berkeley. He thought Vint was responsible for it. And
Oh yeah, he was very angry with me about that, and used to periodically, you know, poke me in the ribs and say, you know, you cost me a bunch of money. And of course, later he admitted that he'd actually made $1 million off of his own implementation. It was called Unit or something like that.
so you cost him all the additional money he didn't make.
I'm sorry?
You cost him all the additional money he didn't make.
Yeah.
But meanwhile, I don't think he really appreciated the fact that you had nothing to do with the Berkeley decision to go forward,
yes,
because
that
it was all handled
by the time that was
Dwayne.
happening, I was at MCI.
Yeah.
But in any case,
So,
both the workstations, the Berkeley release, and local area networking, Ethernet especially, contributed enormously to the rapid spread of internet technology, at least in the research community, because they could buy this stuff off the shelf.
and eventually everywhere else.
Yeah. Well, I'd like to move to the next major phase in your career, Bob, because you left DARPA at the beginning of '85 or end?
September 1985.
End of '85 or near the end, and started a company called the Corporation for National Research Initiatives. What were you thinking about doing? What was motivating that particular path?
Well, I left in September. I actually stayed on as a consultant to DARPA for a while there. I was trying to help Saul Amaral take on the job, so I actually was sort of full-time at DARPA for a while after that.
Saul had become the director of the Information Processing Techniques
Right.
office?
Saul had been a professor at Rutgers, and he came in to replace me running the office, so I actually was helping him. But just to pin the dates down, I filed the papers to incorporate CNRI, as it's now known, on January 29th, 1986. And the reason I remember that date is because, just like I remember the date of my mother's first attack, was because it was Roosevelt's the day that he had passed away. This was the date that the Challenger exploded.
Oh, geez.
And as we were going through the papers, we heard
Wow.
the announcement of it, so I'll never forget that.
So you've just had the 20th anniversary of CNRI this January, is that right?
Well, it depends on what you think is the start date.
Well,
We actually,
an incorporation date is at least one milestone.
yeah, so that would have been there, and maybe we should still do something, although we haven't yet. The first operations didn't occur until May of '06. At that point, it had one employee, not doing much, I might add. In June of 1986, we got employee number 2, namely you, Vint Cerf, and I think we got employees 3 and 4 a couple of months later. So, I mean, during that period, CNRI was born with the goal of focusing on fostering R&D for national information infrastructure. I need to say a little bit about my motivation for why I did that. I would have preferred, quite frankly, to do that out of DARPA because we had a large budget. We had the imprimatur of the government. It's much harder to make infrastructure things happen in the country when you're one of many in the private sector. I mean, it's one thing to be respected. It's one thing to have a little bit of capital. It's one thing to believe you can do that, but to really do it effectively, it needs a sustained push over a long time. And government is able to do that. That's how many of the infrastructures that we know were put in place. But the Reagan administration's view was that this was industrial policy, that if we're going to create infrastructure, the private sector should do it. I mean, the arguments made perfect sense, except that it was very hard to do because the private sector didn't see it as their obligation. And I had discussions with many people, many CEOs about that. They all thought, well, it's a great idea. How many of them really understood it? I don't know. I know that a number of people told me 10 years later, without naming names, that when I first told them what I wanted to work on, which is the national information infrastructure, they thought this was the equivalent of sort of mining the clouds for precious materials, that it didn't seem like there was a there. But of course, people weren't thinking about internet. They didn't know about what infrastructure really was. And even today, if you said to somebody, give me a good definition of infrastructure, they would be hard-pressed. Even the notion of what a distributed system is somewhat elusive. I remember having discussions about even that topic with various people who were very good technically, and I said, in DARPA days, I wanted to set up a program on distributed systems. They said, well, we already have them. I said, can you give me one example? He said, yeah, well, we have these sensor systems. We have sensors all over the ocean, and we bring them back to this machine. They compute here, and we have these seismic arrays. We bring all the signals back, and we compute there. And I said, yeah, but that's not a distributed system. He said, yes, it is. These sensors are all distributed. And so then you get into the issue of what does it mean to be distributed, and what does it mean for them to have to work together? And that's only the starting point for getting to infrastructure. Because there are many people who say, well, aren't memory chips infrastructure? You say, well, sort of, I would say they're infra stuff. They're not structure. They're
a new term in our vocabulary.
It's like oil is infra stuff for the, the road system, the pipeline. But it's very hard to describe it. And it was especially hard back then because there were no good examples that they could typically relate to. The ARPANET was a research project. Probably wouldn't be more of them. Excuse me. So it was a hard message to get across. Most people didn't understand it, and therefore there wasn't a lot of support that I was getting from any place for this as an idea. But my thought was this was sufficiently important. I guess I hadn't internalized how hard the sell was going to be. I might have been still in the mode of saying, they're just not getting it, I should try harder. But I hadn't yet figured out how to make the pitch so that people would would latch on. And I went to a variety of organizations trying to convince them. They all said it was a great idea. They really did. I had no feedback that says, really bad idea, don't do it. But they weren't necessarily willing to pony up any funds. So we raised enough initial funding to get the place going. People that were particularly helpful were IBM, Ralph Gomery, committed to help. He said, you're going to have trouble with other companies. Digital Equipment was very helpful. Sam Fuller and I guess Gordon Bell must have been involved. Xerox, in terms of Bill Spencer and maybe some of the senior people were very helpful. MCI was one of the early funders. I would single out Dick Liebhaber there, who decided to make an investment in, and I think it was more an investment in that case in what you were trying to make happen that he believed in, but they were a strong supporter for a long period of time. Belcor, mainly through a number of people who helped to do that. Dave Sienkoski for one. I'm sure George Hellmeyer and Bob Lucky were helpful. Bill Newport, who was then a senior VP at Bell Atlantic, and Bell Atlantic itself, which is now, of course, Verizon. So those are some of the initial folks that helped us get going with enough support that we could really launch CNRI in at least an organizational way that was effective. But the problem I ran into was it was too hard to raise the kind of money to run a really big national program. Could I have done it at DARPA? I think given the political context, the answer was no, because it was sort of ruled out. But we were also facing a series of other things that were emblematic of the times. First of all, the Reagan defense buildup had just about played out. By the time I sort of left at the top of the build-out, so there was really no more new money going into DoD at that point in time. Number two, so I knew that we would be in defensive mode for the programs that we had created, and since the other offices at DARPA had not gotten a big part of it, they would be inclined to go after a fixed pot, for more share for their new ideas too. So this would be totally in digging in your heels and defending things, but we had some more issues on the table. Graham Rudman was on the horizon, and it eventually came back and bit DARPA pretty heavily. Number three, there were an increasing number of black programs that were being started, things that I didn't know about, couldn't talk about if I did.
By this, you mean
These were
classified programs?
Classified programs of one sort or another that I don't even know what they were, because I was never privy to them or read into them, but there were many of them for which funds needed to be found if they weren't separately appropriated. And then finally, we were starting down a path that we hadn't seen in our field before, where there were earmarks for things. I guess you colloquially call that pork. But, and we were faced with some of that as well, coming down the pike. So I just knew that the difficulties of maintaining this were going to be totally in defense mode, no new things, and that just wasn't me. I mean, not that I couldn't have done it, but I had all these ideas percolating through my head of things I wanted to do. And that was another motivation for leaving to start CNRI. So I couldn't do what I wanted to do, and I couldn't do anything new. So, it was time for new leadership at DARPA, I felt. Besides which, I had been there 13 years at that time.
It's a long time.
Which, by today's standard, is 6 sigmas behind, past the normal lifetime. And, it was the right time. I wasn't drained. I wasn't out of ideas. I was motivated to do it, but the timing was right for me to leave. So I set up CNRI, and I think we've made major contributions over the course of the 20 years that we've been in existence. Some of them you were very helpful in making happen. I'd be happy to recite them, because we're talking about the organization, some of which I was directly involved with. But I think on balance, it was a major assistance to the country on a number of different areas. Today, we have major efforts in microsystems and nanotechnology support to the whole country. It's sort of like a MOSIS for micromechanical design, which is a very interesting problem in its own right, because unlike VLSI, where you can announce a CMOS process and a lot of people could design for it, every design in MEMS and nanotechnology sort of requires its own process. So it's like programming your foundry, like you'd program a computer, putting that in place and then managing the designs through it. So we've been doing that now for about 7 years, and it's growing fairly rapidly. We're trying to make it self-sufficient and maybe turn it into its own little, standalone activity. It's been very successful, and I think it's tremendously helpful to DARPA, but a lot of other people who don't have government support. As you well know, we provided the major support for the Internet standards process. This was an area that you and I talked about back in the early 1980s. NSF needed the help. They came to us and asked us. A few times we declined because we thought it was too administrative, not research enough. But finally, we acceded and agreed to do it. And I think we did a very good job for a long time. We did it under a cooperative agreement with the National Science Foundation through 1997. You were the PI on that for a number of years. We had, I think, several other people followed it. And in 1997, we put that activity in a separate subsidiary organization that I asked Al Veza from MIT to come down and run when he left being the associate head of the Lab for Computer Science. And that continued to provide the administrative support until literally last December, when we sold that subsidiary to a local company called Newstar so that they could continue on. So we're no longer in the process of administering that, and the locus of support for that is now really coming from the entire community. So we took all the intellectual property that we held and we put it in a trust. It was an idea that some people didn't describe it in quite that way, but Patrice actually took that notion, formed it in a way that was workable, and made that happen. So we put all the intellectual property that we owned in the trust. We got the Internet Society to put intellectual property that they owned in the trust. And the IETF community as a whole now has the leadership for it, and we're completely out of it at this point. So in some sense, we kind of went soup to nuts on that, and the thing continues with a life of its own at this point. We'll have to see how that plays out.
I was about to ask, first of all, just on the IETF stuff, if I remember right, Phil Gross was the first executive director that we hired to run the Internet Engineering Task Force effort. And then when he departed to be vice president of ANS, Advanced Networking Systems, we hired a guy named Steve Koya. So CNRI has really had a very long history in the IETF area.
Let me just sort of dot some I's and cross some T's there. The IETF, as I said earlier, really started as one of 10 task forces to sort of maintain the punch list for the original Internet Activities Board. As that grew in time, it took on a larger set of responsibilities. Phil was not the first head of that as a titular group. I think, in fact, maybe Mike Corrigan came in for a while.
Mike Corrigan was first IETF chair.
And then Phil sort of took over that activity sometime, I would guess, late 85, early 86.
He actually supported, he was at MITRE, and I think
MITRE
Corrigan had him under contract, and so Phil was supporting Mike when Mike was formally the chairman of the IETF.
That's right. And Phil then was recruited he was sort of doing it without any direct support, because all the people that were participating in that were either funded by corporate support, to the extent there were corporations involved back then, but many of them were just supported by DARPA on legacy funding and contracts that were about to expire. So this did not have any long life continuity. Of course, NSF decided to come up and pick up the support for that, and they ended up funding CNRI to do that. So that kept the activity alive and productive going forward. So by the time Phil had taken over, he was still at MITRE, and he was brought into CNRI to essentially run that day to day. It was under this cooperative agreement, but Phil was the chair of the IETF. Phil was therefore handling, under your oversight at that time, both the technical and the administrative responsibilities for the organization. It still had a lot of technical folks involved, so he wasn't doing everything, and in fact he wasn't doing everything administrative either, because we had support there. But there were, the locus of activity was at CNRI for both of them. When Phil left, he was replaced by Steve Koya, who had come from MCI also. I think you knew him before well and ended up recruiting him. Steve became the first executive director.
That's right.
Phil, there was no such title before because Phil being the chair of the IETF, what was Steve's role? He wasn't going to be the chair, so as an executive director, he managed down the administrative role. So at that point, which was roughly 1991, CNRI basically allowed the technical aspects of that to go with Phil, and I recall the discussions that you and I had as to whether that was a good thing to do, whether we should try and retain it, because our agreement with NSF basically, you know, empowered CNRI to create a secretariat for the IETF and the IAB, and therefore we could have argued relative to that contract that we should retain it at CNRI. And I think you were pretty persuasive in saying, let it go. I'm not sure whether I would have made that decision on my own, but I probably would have come out there in the final analysis because there was no good alternative. Phil was liked, he was doing a good job, he wanted to continue it. Al Weiss, who was the head of ANS, was willing to let him do that. It wasn't actually clear what a better solution would be, so I probably would have come out in the same place. But anyway, that's what happened. So Steve came in as executive director, and he ran that operation as the executive director until he left, basically, which was in, I think, maybe early 2005 or late 2004. So he was there for quite a while.
So, I'm sorry, go ahead. Well, if we were to go back to the first year of CNRI, if I remember right, one of the things that was a highlight from my point of view was an interview, or a hearing actually, it was a Senate hearing, when the then Senator Al Gore held, and you were one of the witnesses at that hearing. And my recollection is that that was the first instance of the term information infrastructure showing up, at least in the recorded vocabulary of the annals of the Congress. Do you remember that particular hearing?
Yeah, I do. It had to do with the formation of the high-performance computing program, which was I used to think of as a follow-on to the strategic computing, but it was sort of broader in the government. So it wasn't just a DARPA program. It had many, many participants, including DARPA. And as they proposed it, it was an intended response to a charge that Al Gore had made to the administration to worry about linking the NSF supercomputer centers with fiber optic links. And the administration had chosen to respond, and they put together a plan. In fact, I remember the very first plan that they put together really started out under the auspices of FICSIT, I think, the Federal Coordinating Council on Science and Engineering and Technology. But there was a plan that was put forth, and instead of just focusing on what Gore had asked for, it came up with a much broader agenda. It talked about, you know, not only building hardware, it talked about software systems, it talked about even human factors, you know, some of those issues. And so he held the discussion to open it up. You know, well, I asked for this, and you came back with this, and what's the rationale and motivation? And I believe that was the session that I participated in. And that was where the topic came up. And I remember raising the subject, and I remember at the time he asked me if I could give him 2 or 3 examples, and I think I did at the time. Probably one of them was digital libraries, one of them was a national medical exchange, so you could find medical information. And I don't remember all the others, but when the thing ended, he said, well, just for the record, could you give me I think I said to him I developed a whole list for the National Academy back then. And he asked me if I could give him the whole list. And I said, be happy to, and I later did. The thing he was referring to in the National Academy was actually interesting because, you know, the kind of things that we do have been misconstrued by so many people over a long period of time who just didn't know what they were or didn't know how to bin them, what bucket or what box to put them in. So one of the things that the Academy did was they reconfigured and restarted something called the Computer Science and I think it was called Technology Board
Are you
originally.
sure it wasn't telecommunications?
It's now telecommunications,
Oh,
but I
okay.
think it was originally the same acronym. You know,
Okay.
like IAB continues, CSTB continues, but the words mean something different. So, and I was one of the original members of the reconstituted board, chaired by Joe Traub, who has been until recently, maybe still is chairing the current CSTB, although there were other chairs in between. And one of the first things that we did, and it was a fairly august group of people, was say, what are the things that this board should be worried about? And this was 1986, I believe, and I had already started CNRI, and so we were now known to people there as focusing on the national information infrastructure. And we were the only ones who were doing it because it was sort of nonprofit in the national interest. And that topic came up, it was put on the board, and it was rejected. Not necessarily by the people in the room, but the view was that the National Academy should not be focusing on something that was the proprietary interest of any one company. I said, well, national information infrastructure is like working on clean air, you know.
Yeah.
It's something that's going to be a benefit to everybody. It's not a product, or it's not something we're selling or unique to us. Well, a number of years later, the same topic came up again, and it got on the agenda unanimously, and nobody could ever remember why it didn't get on originally, because they were worrying about why isn't it on at that point in time. So sometimes that happens. I'll give you one other example. I mean, it sounds a little embarrassing in the retrospect of hindsight, but it was the reality that we were dealing with then. Nobody knew what infrastructure was. So we had this infrastructure thing on the board, and we're trying to figure out, well, what should we focus on doing? Well, we needed to get support for this effort from the board under which the CSTB was located. I think it was the Physical Sciences Board. And so Irving Ledowski-Berger, who was then a member of it, and I were charged with going and giving the briefing. And the first question that came out was, well, what do you mean by infrastructure exactly? You know, what is it? And so there weren't, as to my recollection, any computer science folks on the board, or if they were sort of people that worked in multiple areas, of which computing was one. And so we kind of looked at each other, how do we want to try and explain this in concrete terms? So we said, why don't we try email? She said, well, email is a good example. I mean, people knew about it, people were using email, and there are, you know, national issues and policy issues having to do with getting email out, you know, into the country and interoperable systems and kind of dovetailing everything. And the reaction at that time was bewildering to both of us, because they said, well, how does this help the scientific community? And we said, well, you know, the physicists can use email, or the chemists can use email. And they said, fine, if you want to work on email for physicists, that's fine. If you want to work on email for chemists, that's fine, but you shouldn't work on email in general. And we said, it's the same problem. I mean, physicists are real people in their other lives. Physicists often talk to non-physicists. Everything is interoperable, and that's what makes infrastructure good. You could talk about, you know, the highway system for doctors, but it's the same highway system that the taxi cabs and the truckers and everybody else uses, so you can talk about that. It makes no sense to do that. Well, we didn't make any traction, and it disappeared. But a few years later, the same question was put forth, and at this point there were no objections because it seemed logical. So I think it was part of the education process of people to figure out what we're talking about, what it means. And we've seen that oftentimes. It's one of my bigger frustrations. I've learned to deal with it, that sometimes a vision that you can see is hard to convey to somebody else, because I lack the vocabulary to map it to what's in their head. And it's like trying to teach quantum mechanics to somebody who, you know, is observing the physical world, or maybe even is talented technically. It takes some getting used to, because some of the notions are sort of not visible, counterculture, and after a while you sort of start to think in those terms.
They're even counterintuitive. One thing I would like to achieve in this interview, Bob, is an appreciation for the scope of work that was done at CNRI and or is still going on. The things that come to my mind very quickly are things like digital libraries, the Gigabit networking program, collaboratories, the interconnection of MCI mail on the internet. You mentioned earlier the microelectronic mechanical systems, the knowledge robot ideas that sort of came out of the digital library work, the digital repositories, digital object identifiers, and the systems that go along with that. I'm not sure how to how to try to capture a lot of that, but first question is, what did I leave out? And second, of all those various things, are there some that you particularly would like to make sure we capture in this interview?
Well, you left out some, but I don't know how important it is to be exhaustive here. Let me just assert that we've covered our role in helping the internet to become real, and especially our role in the internet standards process. I'm not going to go back to the the MEMS microelectromechanical work and the nanotechnology work, because we could spend hours on that subject alone, and how that works and how we can help people in that area, sort of like in a MOSIS system. Let me start with the Gigabit Testbed project, because that was an early one that we got started. As part of that program, which was funded by the National Science Foundation, we funded, in fact, when I first wrote the proposal for doing this, it was in a very abbreviated form, and it was intended for NSF to do the work on their own. I was trying to assist Eric Bloch in understanding how NSF itself could help the community. If they're going to get into networking, make a big step. Don't make a little one. And I suggested that they go down that path because I thought the technology was able to be harvested. It wasn't quite out there yet, and rather than focus on something more near term, take a big DARPA-like step. And I think the sense at NSF was that they don't know how to do that exactly, that a lot of the technologies in the research labs, you can't buy it, they don't have the staff to manage it, sort of like DARPA might manage a project, that what they could do is procure a network. And so they made the decision during this whole process that they would in fact put in place a 1.5 megabit net, which became the NSF net, and get behind that, which they could procure, and they could manage the procurement. And somehow they left it that they would have a separate research program to deal with gigabit nets, but it wouldn't be an operational build of any sort. And I recall that Dave Farber was actually the first one that approached me on that topic. I mean, I had been interacting with Eric in any event, because I knew him from
Eric Bloch?
Eric Bloch. I knew him long before.
Eric was at the time the head of NSF.
He was the director of NSF.
Right.
He had just come in 1984 to head NSF. And I had been interacting with him when I was at DARPA to just try and help him. And Dave came and said, they're going to go build a 1.5 megabit net. I think that CNRI would be a good place to help them make a gigabit capability happen as an R&D thing. And I remember looking at it and saying, well, if they're going to go do an NSF, then maybe we want to build the 1.5 megabit one. That might be interesting. And as I recall, you at the same time were probably having discussions with DARPA about doing a 1.5 megabit thing for DARPA, which decided that they'd been there, done that, they're going to move on to the next thing. So they didn't bite. So NSF funded Merit to create the NSF net, and I put together the proposal with help from many people in the community, because it was representing different points of view as to how to do this. That became the proposal. The actual way this worked was quite interesting, because I wanted to do a solicitation. I didn't know what all the good ideas were. And this was not intended to be a Bob Kahn figure it all out and go implement it project. So I wanted to put out a call for white papers and find out what the ideas were. But NSF didn't have a mechanism to allow that directly. So they said, you can't do that, you got to propose something specifically if you want, and we'll consider it. So I said, fine. So I wrote a proposal. I got significant input from Dave Farber in the process, and I got letters from people who said they were willing to participate with us. I got it from AT&T, and I got it from IBM, and I got it from, I don't know who they all were at this point anymore, but a lot of the big players said they were willing to work with us. They'd supply people and technology and the like, and I got something like 8 or Washington universities to say the same thing. People like John Turner from Washington University, and I think even somebody from Penn, although I don't know if it was Dave himself. Dave Clark up at MIT. There were a number of the relevant players in the field at the time, or many of them. And I was willing to proceed on that path, or I wouldn't have sent in the proposal, but I kept thinking, you know, maybe there are better ideas out there that I don't know about. This is just a selection that I made based on what I now know because I was forced to make a selection. So I sent the proposal into NSF, and it came back basically saying, well, we like the idea, but we don't understand why you picked that set of participants. This was couched. I mean, this was not, I mean, they knew what was going on here, and they said, you know, we'll give you some preliminary funding to go find out what the best ideas are in the country. So I think they funded $500,000 of what eventually was a $20 million grant. And we put out a call for white papers. We ended up being enabled to do what I wanted to do in the future, but because they directed it rather than I proposed it, it was apparently allowed. Although I understand there was some debate within NSF as to whether this was really an appropriate path to follow at all, and that maybe NSF should really be doing all of this and the like. And the way I did that was kind of interesting because I inverted the process. So normally the government will have an advisory panel consisting of people from the universities and research labs that know about the area, give them the technical evaluations, and the government makes the decisions. I flipped it around. I had an advisory panel made up entirely of government people. Some from NSF, some from DARPA, some from DOE, some from NASA, some from NIH, right across the board. And there might have been one or two private, I think one or two private sector folks were involved by choice of the government. And they actually did the vetting of all the proposals. And they broke them into three categories. The A category, like must fund. The B category, okay to fund if you need them and don't, you know, and have extra money. And the C ones, which were sort of, these are really bad, don't even consider them further. And so we put the program together mostly from the A and some of the Bs. But I then had to go out and solicit carrier support. And I remember having a discussion with Eric Block, who called me to say, Bob, we're going to fund this. It's a $20 million grant from NSF. Was a large grant. I think it was $16 million initially, and included research. So the actual proposal was more. They took out the research pieces and just left the testbed part in. And they basically augmented it later with some more money. So that's how it ended up at $20 million. But that was probably worth 4 times as much if you went back 20 years. And Eric and I had a discussion on the phone. We said, Bob, we've decided we're going to fund this. And he said, it's unusual because normally we ask for all the commitments from all the parties ahead of time, and you don't have them. And I said, I can't get them if I don't get the government money. We posed 5 test beds. And I said to him, quite frankly, I don't know that I can create all 5 of them, but I think I got a good chance to get at least 3. And I'd be very disappointed if I don't get 2. He said, I just want you to agree that you won't spend all the money and accomplish nothing. So he was kind of worried about how it would look over there. And I said, you have my agreement. In fact, I was very miserly on how we spent the money until we essentially locked in all the agreements. And so we had discussions with lots of players. In the final analysis, there were more than 40 organizations that were involved. A lot of carriers, some computer companies, some universities, labs. I think we funded about 10 or 12 of those, and the rest were voluntary contributors. And we built 5 test beds, and they all happened. We got 100%. And out of that program, some very interesting things happened. One was the first deployment of an all-optical link between Wisconsin and Illinois. AT&T built that one with the erbium-doped amplifiers. It's the first deployed operational link anywhere, I think, in the country. No electronic repeatering, I mean. We had the first deployed ATM switch in a carrier central office. It may have been the first OC12 switch. I'm not sure whether there was an OC3 one before. This is a switch that worked at 622 megabits that was deployed in one of the carrier offices in North Carolina as part of a test bed there. We funded Illinois to build a point-and-click browser for, they were building a database of their simulations, and they kind of wanted to work on digital libraries as part of that. You may recall that CNRI actually built a point-and-click browser for the internet in the late 1980s. Not very well known, but the particular browser that we built was part of an effort with the National Library of Medicine.
Remember that.
And when we demonstrated it, the reaction that we got was that doctors would not rely on point and click and using mouses, and we needed to have a forms-based system. And so we ended up basically rebuilding that into a forms-based system for access to Medline. Now, Tim Berners-Lee says he built an early point-and-click browser for the web on a Next machine out at CERN. I have a feeling we might have been earlier than him, but neither of those actually made it out, because the one we built was sort of unique to the National Library of Medicine and involved generating nobots behind the scenes and automatically figuring out how to translate what ended up being form-based commands into database commands of different database systems. But we funded Illinois to build a point-click interface to their simulation stuff that was stored elsewhere. And I have Charlie Catlett, who was then the manager of that project at NCSA, basically saying that the one thing he regrets, and this was like 1993 or maybe 1994 at a major public conference, I still have it on videotape, that they did not decide to hook that browser up to the web protocols. He says they debated it, and they made a conscious decision not to, because they would have had to reprogram all their simulations in HTML, and they thought that was a waste of time. So they didn't do it, and these guys down the street picked up on that, and I don't know the details of whether they used their code for experimentation or just did a clean slate implementation, but they built what became the Mosaic browser. So I think, you could argue that that program was the genesis of the Mosaic browser at some point in time. Of course, NSF was involved in funding both, so NSF can take credit either way. But the Mosaic browser really changed the landscape, and it's what turned the web from something that was just out there and not really making much progress into something that your grandmother could use, because you didn't have to learn procedures and you didn't have to wire things up. You could now punch a button and get something, and so it was a major social contribution to make accessible something that you really needed to be a computer scientist before, or have the same mindset to be able to use. So I think that was an interesting thing that happened out of that. We had, a number of other things that we had some large number of supercomputers in one of the test beds that linked JPL, Caltech, the San Diego Supercomputer Center, and Los Alamos, all hooked up doing really interesting things like, evaluating hydrogen fluoride laser dynamics, like how does the lasing occur in high-powered lasers, weather simulations. It was really a major effort. And of course, one of the test beds was totally focused on networking research. We were trying fast switches of different kinds involving IBM and Bellcore and MIT and Penn. So all in all, I think that was a major project. I think it put high-speed networking on the map. And I think it wouldn't have happened without some major commitments by carriers to help out. MCI was a major contributor to two of the test beds. The one up in the northeast corridor called, I think we called that one Aurora.
Aurora, yeah, I should
and
remember
one
this.
out,
That included the Bellcore people,
Bellcore
as I
and
recall.
IBM,
Right.
MIT and Penn. And the one out in the southeast, which we called CASA.
We had another one called Blanca, as I recall.
Yeah, that was some combination of Bell Labs, NCSA, University of California. I mean, it just sort of worked out. And CASA was from like Caltech and San Diego. So, I mean, the names just sort of showed up, and it looks like they were designed to be Spanish in origin, but it didn't quite work that way. And so I think that really did put high-speed networking on the map. Unfortunately, having now built those nets, in the mid-1990s, there was no program to fund research on high-speed nets. It didn't materialize, and the bottom line was nobody took the initiative to find that funding at that time. The carriers said, well, why should we keep these nets up if there's nobody funded to make use of them? We ended up dismantling the whole thing.
Yeah.
So a few years later, they set up something called the Next Generation Internet Program or something like that, and they suddenly put up money for building it, but now we had lost the commitment of the carriers to actually make that technology available. And so, you know, we are here today in 2006 with less capacity, at least in some places, than we had more than a decade ago within the research community. But people now appreciate that high-speed nets have some value, including the industry. So maybe we lost a decade, but my guess is we'll pick up and continue on a path of progress. So the Gigabit Network project, I think, was a really important one. One of the things that I don't really take a lot of credit for in terms of the vision at CNRI, but was true of an individual, was we helped to take a language that had been incubated at CWI in the Netherlands and grow it into a major prototyping language called Python. It was really the work of a single individual and his band of merry men, Guido van Rossum, who I believe is now a Google employee.
I think that's right.
And he generated a marvelous language, which is one of, when people list the languages that they'd like to make things work with, they almost always list C++ or C++. They almost always list Java. They almost always list Python as three of the critical. Sometimes they'll list other things like Perl and the like, but I think that was a major contribution. And the hardest part of that contribution, interestingly enough, was something that Patrice solved with a little help from Guido, which is, for all the while he was working on this, I was not willing to license the software. And the reason I wasn't, because every time I went to Patrice and said, we need, this is my wife Patrice, to write a license, she says, well, do you own it? You know, where did the pieces come from? You know, and so I'd go to Guido, and he'd say, I have no idea. You know, I came over the transom, my friend Joe here, and then the answer was, well, did they give you the rights to use it? Well, no, I mean, they're just my friends. So we had all this stuff, and so I just was not able to, I mean, it's not that I was refusing in some abstract sense, I just didn't have the ability to do it because I didn't know whether we owned something to license. And so when Guido finally decided to leave, which was in March of 2000, this was just before the dot-com boom, he was going to...
The dot bust, yes.
Well, yeah, just before the bust. Before the boom busted, he had gone out to take a job at some Silicon Valley firm, which 6 months later was bankrupt. And so he didn't make his millions or billions out there, and you know, eventually ended up finding a job at Google after 3 or 4 intermediate places. But the bottom line was he eventually understood the need for some regularity. It was not an easy thing for him to decide, but he went back to all his friends. He got, you know, they were kind of blankets to the extent that I have any rights in anything that you might have of mine relating to Python. I hereby, you know, give, so they couldn't even say what it was anymore, and it had been so iterated on, but we got to the point where at least we felt we had confidence in what we had. And since some of that was derived back from CWY days, Patrice went back to the Netherlands, and she had to find out what were the laws applying to employees back then. You know, how do you find the 1984 Dutch laws? And it turns out they got it from different places, and so, but we worked it all out, and finally we were able to license it. And then the most interesting issue was they said it really needs to be compatible with the GPL, that license that Richard Stallman and the folks at the Free Software Foundation had been generating.
Why is that?
Because a lot of the people who use Python also use GPL code.
Oh. And so the results of their work get sort of conflated. Oh my.
That's right. And the GPL regs, which in fact I think were part of the reason why the whole open source movement started, said if you use any of our software in this collection, I think that they later modified their rules somewhat, but back then I think it was, if you use any of our software, then anything you do with our software has to be put back in the pool.
Yes.
So it wasn't very friendly to companies trying to build new products, systems where they wanted to own their stuff or maybe even sell it. And the open source thing was intended to get away from that. They wanted sort of transparency in a lot of different dimensions, like at least let us see the code and don't make the licenses ununderstandable and things like that. But I don't think they explicitly prohibited you from owning it yourself and selling it and things like that. So it actually was a very interesting fork in the road that was taken by those guys back then. So I think that's something we can be proud of. It's, again, thing we did for a while, and it's got some lasting value out there. So I think that was good. The thing that I'm most involved with and in many ways most interested in, and I think I'm pretty happy with the way it's gone, is the work that we've been doing on the digital object architecture. It had its genesis in work that we had started on digital libraries. In fact, you were intimately involved in that back then. And we were starting down the path of thinking that the way to deal with libraries in the network environment was by essentially sending out these entities, mobile programs that could look at different places, pull back information and bring it back. And we actually built some early prototype systems that could go out and do similar things like name kind of who-is-like databases, bring it back. They all came back in different forms, put it in standard forms. You wouldn't know you were dealing with multiple things because these programs would be going out and doing different things on your behalf. We ended up in the early 1990s getting the first serious funding to work on that. And it was part of a effort called the Computer Science Technical Reports Project that DARPA funded. This was before the web had emerged, because that really didn't become visible publicly in any significant way until sometime in the 1993 timeframe, after the work at Illinois had become very public. And as part of that project, we were asked by DARPA to work with a set of 5 universities who all wanted to digitize their collections. I mean, the historical stuff. And DARPA really didn't have the time or the energy to get into it. The program manager at that time was a gentleman named Brian Besch, who was working in distributed systems, and he asked if we were interested in that, and I said, yeah, very. So I actually wrote a proposal to work with that community, and I called it something like Linking Electronic Libraries. And the model that I had at that time was that if we could enable people to build different electronic libraries, then there was an interesting challenge that was very much like the original internet problem that we focused on, where you didn't want to have to deal with somebody in this collection of networks by specifying what net they were on and what path to get there and what protocols to use to talk to them. You just wanted to send the email to them and have the system figure it out or whatever. And so the whole notion here was that if you had these different systems, and abstractly I was thinking of them as different informational systems, although we ended up focusing on digital libraries, which was a more manageable subset, sort of like countable numbers rather than uncountable. Still big. The whole idea was if you had different information systems and you wanted to pose a query for which the answer was in the collection of systems, how could you do that in a way that would not have to have you know about all the details of these different systems? But by virtue of having the digital library example in front of me, it gave it a lot more specificity. I could start asking, so instead of asking an abstract question like, what was the nature of the Greek city-state? Or, how many ways can I count such and such? Or, what's the nature of life? Things that, there may or may not be answers to, and the question domain could be so open-ended. With the digital library world, you were much more focused, like, get me today's New York Times, or get me the memo I wrote yesterday on such and such. Now, it could be more detailed. I mean, you could ask a more researchy question, like, what was Thomas Jefferson's favorite reading material? But my view was there was a very concrete, focused problem one could work on. Let's say that I knew exactly what I wanted. So somehow somebody had done the research, and I knew what Thomas Jefferson's favorite book. How could I get that book if it were on the net in digital form? And so the thing that we created, in fact, was sort of part of the thinking all along, was that these entities on the net would be digital objects, and these digital objects would all have identifiers, and those identifiers could then be used to figure out where they were on the net, because you'd have a general purpose resolution system. If you send an identifier into the resolution system, it would give you enough information to have the machinery find it. Like here are the 10 places that have it. They might have IP addresses, they might have DNS addresses, they could have handles, and they could have any way of identifying the locations, but you could then take the one identifier and find what you want wherever it is on the net. Furthermore, you could do other things. We thought about, you could authenticate the material when it got back, because you could put authentication information. You could have security of all sorts embedded in there as well. So that was sort of the basic idea. So we took on ourselves to work on this problem of sort of the generalized architecture for linking these different libraries. And I saw it intrinsically as the internet problem reposed at the application level. Mm-hmm. So instead of having packets moving around, you have digital objects. Instead of worrying about resolving IP addresses or DNS names or using routers, you'd have a resolution system. And we actually built such a resolution system. And we call these things handles, when the resolution system was called the handle system. But what it really is a general purpose resolution system that will resolve anything. And in fact, we even put a big chunk of, if not all of, the DNS on there and getting ready for the Y2K transition with help from Network Solutions. And we showed that the system could deal with that as easily as anything else, except that, you know, doing it to do DNS resolutions was like using a supercomputer to add 2 and 2. I mean, you had more power in the handle system than you needed for just that task. On the other hand, running the handle system costs like 4 orders of magnitude less than running the DNS system, because, you know, there's just not that much cost in running it currently. But it's managed in a different way, and all the management is built into the system. So that was one of the pieces of the architecture. So we knew that identifiers would be important. But what I did with the university community was I funded them not only to do the digitization, but I asked them what research you would do on that. So they all built, you know, their own libraries, and all different, and they all proposed research programs to use their collections once digitized. And so some very interesting things happened. So Carnegie did one that involved video and audio stuff, and Berkeley worked on certain environmental stuff in the state of California. And so everybody had, Stanford had their own set of proprietary stuff, student theses and the like. And we put that program in place, and it provided the support to go work on it. I was very interested in how, well, there was a lot of disagreement up front on how the system should be structured, and particularly what the role of semantics should play in it. There was a lot of commonality on other grounds, and it brought to mind more clearly than ever the importance of intellectual property and rights clearances and all that.
Okay, so we had just gotten into the digital objects world, and I'm wondering whether you'd like to say anything about you were talking about the concepts, but these notions are now actually in use.
Yeah, so let me explain what's happened. I mean, the whole idea of the digital object architecture is that you have these objects, they are structured, they're parsable by machine, they can therefore be moved from machine to machine, and the elements of it understood. The elements are not designed by standards. The structure of it is designed by a meta-level standard, so everything is sort of type value pairs, and you can define new types and resolve them through the resolution system. So once one of these objects shows up, you can figure out what the object means, because it's in this meta structure. The identifiers are critical to these objects, just like file names are to files. And there's a resolution system that resolves it. Well, we built the resolution system. We call it the handle system. It's been on the internet now since 1994. For a long time, ISI ran a part of it. There was an agreement I had with John, because he actually wanted to move over toward handles, but said the politics of getting this through the system is so impossible. And of course, he was in the process of trying to disengage even. But we've had it deployed. It's been 7 by 24 for about a decade now. It's widely used by the publishing industry. But what's even more important is not only do they use the system, but they use the identifier means for all of their electronic journals, or at least the participating sites, which is most of the big publishers. They set up some organizational structures. There's something called the International DOI Foundation, which is kind of like an ICANN for the publishing industry. They like to think of it as broader, but mainly they're dealing with publishers at the moment. They do a few things in that organization, including qualify registration agents. They worry about policies and procedures, licensing trademarks, marketing, and the like. They've got some number of registration agents around the world who they give pretty much carte blanche to work with other parties who want to identify things. So like a publisher, like any large publisher is not one of them, but they could work with one of those parties to identify all their materials. The IEEE, for example, puts out electronic journals. Their goal was, and this was part of the architecture originally, to make it last over long periods of time. I mean, if it's a short period of time, you could do a web-like thing, just sort of cite where it is, and as long as nobody cared in 6 months, that website will probably be good for 6 months, especially if the people there are keeping it up. But the IEEE would like to put an electronic journal on the shelf and have somebody in 500 or 1,000 years take it off the shelf, be able to click on what's on the back and still find it. Just like if this were a library and they kept all the collections on the shelf, you could go to the right part of the library, pull that collection off, and find the reference. They don't want things to somehow disappear. And mobility is probably treatable in lots of different ways, but when you're dealing with objects that are intrinsically dynamic and linked to lots of other objects, all of which can move, building a system that allows this to survive not only movement but technology changes over millennia is a real challenge. But I believe the use of identifiers to do this enables that to happen. I mean, you've got to maintain the system below it, but the things that are embedded in the content don't have to change in order to allow this to happen. So that was part of the design goal for the system, and I think that's what we have out there. So that's the real power of it. It won't be felt, until people are beyond the period where the old systems don't work anymore. But that was one of the goals. So that's been out there. It's widely used, and it has these very nice properties. We also put out the software for it under an open source license, mainly because of the interest of the folks in the global grid community who wanted to be able to use it and give it to companies to do software development. So any company that wants to can take the software and make use of it. The only thing that we collect as part of this activity is a small charge as part of a service agreement to help support the global registry, which is really what you need to know where to go to do the resolution, because unless everything is resolved in one place, you need to go somewhere else to figure out where, and that somewhere else could be a big distributed system rather than one location. Also, because many of the people who are using this system insist on using legacy technology, and I call the web legacy technology because it's whatever it was before the system was made available, we built another mechanism whereby you can get ultra-reliable access to the system through an intermediate level that doesn't require any changes to the current internet protocols. It's a really interesting contribution. It's really only relevant to the web stuff in its current form, but there's another incarnation that's much more broadly of interest, but I don't have time to go into it right now. Another thing that we've done with support from with some industrial support is to look at the application of identifiers and the digital object architecture to the networking part of the problem. We decided not to get into that at all up front because it was so political, there were so many parties, the internet hadn't really taken shape. I didn't want to disrupt all that. But the internet's now gotten to a point of stability. It looks to me like there are real strong interests in trying to reinvent things going forward. And so what we did was, with some industrial funding, we looked at the application of this to network management, network provisioning, and network operations. So it turns out you can not only identify all the information flowing in networks as digital objects, which means that you can store stuff and you can access it, you can put it in archives, and it's accessible for, you can do postmortems after the fact. But literally, you can identify every element of the network as a digital object, even though it's physically on some hardware. It's sort of like, giving, your being an identifier and saying it happens to be housed here right now, but maybe in another life we'll house it somewhere else. So if a router somewhere were to go down, you could literally pick that router up and move it somewhere else. And you don't have to worry about changing all the parameters of everything internally, and because that router in your network concept was a logical element rather than a physical thing, and that physical thing was only its current place of instantiation. You can move it elsewhere. So think about the network as now totally fungible. So it's an area we've been pursuing, and I think it's very powerful. And it's just one more application, but at a lower level. So we've worked on repositories to store digital objects. And we've gone through 3 generations of them. One generation was part of a kind of a monolithic digital library that we worked on with the DoD. Another one was part of a modular implementation of a digital library that we worked on to enable other services to be plugged in by other parties. And the third one was one that we did with some folks in Homeland Security that was a real-time one to keep track of, very high stream entries. If you're dealing with a library, the number of books that are going to enter into the system per second is probably, a fraction. You might have a few a day. You might have even tens or hundreds a day. You're not going to have 10 million a day. People just aren't going to create that many that are readable or interesting. But if you're dealing with, sensor transactions or other kinds of things, you might have very large numbers of things entering into it. So we built a real-time version. Right now, we're working on melding the real-time version and the modular version to build a real-time modular version. And we've applied that in many different contexts. One of the things we pioneered was the creation of compact metadata registries. The organization in the publishing industry that helps them manage their activities is an organization called Crossref. It's located up in the Boston area. Crossref is a very interesting organization because it's got a commitment to help the publishers manage their identifiers in perpetuity. So you might ask, well, what happens if Crossref goes out of business? But that's an organization that's really a membership organization of thousands, or about 1,000 publishers. So they all have to decide to go out of business before that would happen. So I think it'll have some longevity in life. And the way they do it is they will typically charge a one-time fee for working with a publisher. I don't know the details of their business arrangements. I never asked, but let me give you an example. Let's say they charged a publisher a certain amount per identifier. So if you gave them a book, for example, let's say, a simple model might be one identifier for the book, but that means you get the book or the whole book and nothing but the book. But suppose the publisher wanted to transact business on a chapter or a table or a figure or references or whatever. They might want to give out 10 or 100 identifiers to pieces of the book, and generally they'll identify what they want to transact business on. So they're not going to sell you a letter of the alphabet. They're not going to sell you a word in the dictionary. They're not going to probably sell you a sentence, maybe not even a paragraph, and that may even be fair use in some contexts. But they might be willing to sell you a substantive part of it for use in a course or whatever, or a figure, or a cartoon, maybe, in a magazine. So what they would do is have a single fee, or maybe they do it a block grant. We'll do so many books or journals per year or so many identifiers for a set fee. And for that one fee, they will create the identifier. They'll get it into the resolution system. They will annotate all of the pieces in the back. So let's say there are other references back there. They'll put in the right identifiers. They'll make it all work as a clickable. And they will put the metadata into their metadata registry, and they will maintain that for the life of the identifier. So I call it cemetery funding. People don't like that idea, but it's sort of like one payment up time, because you don't know who 50 or 100 or 1,000 years from now would be interested in paying for that identifier, because it was, who knows what it was from way back when. But if you can have one fee and they'll then continue it from then on, that kind of works. So that's the way they work. They pay a small amount of fee up the chain. It would be like, a registrar in the ICANN context paying, or maybe a registry paying a small fee to ICANN per year for what they do. Maybe ICANN could have a different model, but they pay like 4 cents, and it's a declining scale, so when they have a lot of them, they pay less. It's a one-time fee for creating these identifiers. And you know, when all is said and done, that's how the IDF gets its support. But let's say the charge, I'll pick a number. I have no idea what the real number is. Let's say they charge $1.50 for identifier. That does all those things, creates the metadata, puts it in the system, they maintain it forever for the $1.50. They might put on a 4-cent charge, so they might charge $1.54 instead of charging $1.50. 4 cents goes up to the central body, they keep the other $1.50, and they can set their own business schedule any way they like. So that tends to really work pretty well, and it's a model that does work. So we were very involved in helping to create the first metadata registry. The one that the DoD has gotten very interested in this area for managing training and equipment kinds of documentation. And the program is called the Advanced Distributed Learning Program. It's run out of the Pentagon. We actually built the metadata registry for them. It's now deployed at the Defense Technical Information Center, System Center. It's DTIC, the Defense Technical Information Center. They actually keep the materials there too if they're internal DoD, I believe. But they may reference things that are outside that are just useful for what they do. And the DoD has mandated with that registry that there be a specific metadata standard used. It's called SCORM. And they've mandated the use of the handle system, which has been part of what DTIC has been doing for years. They sort of manage that for the DoD. And so it's a nice application of the technology. So the repository stuff, the metadata registry stuff, the resolution system, and we're working on other attributes which would provide advanced services on top of that. But I think the thing I'm most interested in and been very active lately is turning that into an archival system that can last for a very long time. And what we built is a reference model. It's on the internet right now. It runs at 600 megabits a second. You know, we provide, DARPA is handpicking the people to make use of it, and they're going to give it free to some large number for a while. It's got some very interesting attributes of how things work, and the most interesting thing is it allows you to move stuff from archive to archive. So it's got an inter-archive open architecture kind of nature to it that's really very powerful. And so it's something I'm very interested in right now, because the ability to move things in this hyperlinked environment and have everything work is really interesting, particularly since we disentangle attachments from email, and so attachments might go one place and email might go another, and you want it to all play together. I think if there's one message in all this, it's the importance of identifiers, because the technology for how you store stuff and how you parse it and what the particular things mean and what the standards are will change over time. But the idea of having things linked in some abstract level through these identifiers, I think, is a very powerful construct, and one that increasingly over time people will understand the importance of, especially when you don't put semantics directly in materials but use some other external system to figure out how to map those identifiers into the right level of resolution information to take whatever the next step is. It also lets you move things around with impunity, because the identifiers don't change when you move, and the resolution system can sort of do the mappings. So that's one other area. There are lots more that we're working on. We're sort of pursuing, you know, so I would say with some concern on my part, because I always think some level of management is important, and in this world that I just described, the identifier system at some level I think needs to be managed. I don't think you can let it go free form and not know who's where. I mean, that's one of the reasons that ICANN has been so important to the internet going forward for the DNS. But short of that, I'm trying to understand whether there is a model of the future in which everything can be sort of unmanaged. I mean, people complain about the internet today as having nobody in charge, or no one party in charge. But yet there are management structures in lots of different places. How much of that can you actually relax? And how much can you do in the way of peer-to-peer networking such that you end up with a robust system in the final analysis? That's one of the other things we're looking at. So CNRI is into lots of things. I think one of the things that we've done that's really nice is an infrastructure series that we published. We're looking at a number of other issues. One of the ones that we're particularly interested in is, can we do something to affect manufacturing at the level of maybe semiconductors or MEMS or nanotechnology to really make it cost effective to do small job lots. And while part of that has to do with getting cost effective equipment, because almost all the equipment that's made available in industry today is basically in a semiconductor mindset where you want to make 10 million or 100 million things through the piece of equipment. So it's designed for high throughput, and they're high cost, but when you divide it by the number of objects, they come out pretty cheap. If you only wanted to make 500 objects or 1,000 objects, you can't afford to buy a lot of multi-million-dollar machines. It becomes the equivalent of the, why is the proverbial hammer so expensive, or worse? It's because you've got a lot of overhead that you have to then apply, unless you can cover it some other way. But it turns out that even if you could get the equipment costs down to more reasonable levels, they still won't be cheap enough. They've got to be reused. And so the real task there is to figure out how to get the equivalent of what we're talking about in the network, commonality of abstractions so that they can work across multiple platforms in terms of manufacturing process steps, so that given pieces of equipment without change can do multiple kinds of processes, not just that one step, that you can package them up, take this equipment, and in different combinations, piece A, B, and F, put it together to do this generic process or that generic process. And so the real key to making this work, I think, is going to be designing what the abstractions are one level above the equipment, and that's another thing that we're currently working on.
I'm sure that we could go on here, but there's only a finite amount of tape. I'd like to suggest just a couple of other specific things. First of all, with regard to the longevity of property in a repository, one of the problems that has both a technical and an intellectual property element to it is being able to interpret the object after many, many years have gone by. And you can imagine one possibility is you're doing a search of the internet in the year 3000, assuming the internet's still around or whatever its successor is, and you encounter an object which is essentially interpretable by Microsoft PowerPoint 1997.
Try VisiCalc.
Well, that would be another good example. So
do you have a copy of VisiCalc around?
The answer is yes. I don't know that it will execute, however. I have a 5¼ inch floppy disk, which I don't have a reader for, that if I had the right Apple IIe hardware.
So all you do is take your BlackBerry or whatever your device on which your email arrives, and you plug it into this old floppy 5¼ inch reader, and it runs VisiCalc on your attachment, and you're all done, right?
Yeah. So the issue here is not just the physical medium, which I think you could argue could be converted and transmitted as long as you can convert bits into different storage formats. But the problem is, what do you do about the software that interprets the objects, and maybe even the operating system that was needed to run the software that interprets the objects? And the reason it's an intellectual...
What about the hardware on which the operating system has to run?
The house that Jack built, yes. So here's the question. Have you already tackled the problem of obtaining rights to use the software 1,000 years from now to interpret? I'm asking this in part on the grounds that I don't think we're going to be able to always transform a particular object into the next version of something that can interpret it. Backwards compatibility is not always guaranteed. So, for example, Microsoft recently announced that it's not going to support Windows 98 anymore. And so if you don't have any rights to Windows 98, if you don't have any ability to get the source code or do something, it may be that things that were only workable in Windows 98 will never work anymore, or after a period of 20 or 30 or 40 years. Is there anything in the repository ideas that would allow you to capture the the necessary software in order to keep interpreting objects over really long periods of time.
Well, I think this is not a technical problem. I mean, you and I could sit down and we could design a strategy that would do it all, and the real issue is, do we have the right to do that, and do we have the underlying mechanism to capture everything that we need? For example,
that's why I'm
how
asking the question.
I mean, if somebody built the general purpose emulation machine, and then every architecture that were ever put out had the right emulation pattern to it, and we could preserve that over time, we might be in pretty good shape. I mean, if everybody could agree that Java was the answer forever, then all you'd have to do was worry about getting a Java compliant environment underneath it, however you chose to do that. But that's not what we face. And so that's a technical challenge that could be solved with enough time, energy, and money put at it, I believe. The more interesting question is not even can you get the rights to the software, because sooner or later it's going to be out of copyright, sooner or later. So if you're really talking about 1,000 years from now, and you just kept your copy on your machine long enough, assuming your machine still ran long enough to produce it, you could put that in some kind of an archive and maintain it. And there are people who are trying to build, software constructs. You still need to figure out, what are you going to run it on, whenever. But let me assume that problem is solved too. The really interesting problem to me, and the one that we are trying to clear rights to, let me say we will be trying to. We've had some discussions about how to go about this, but ultimately it will probably be up to the lawyers to figure out how, is how to get rights to the proprietary data structures that all these programs use. If you want to generate a good job of building a metadata registry, it's not enough to know that this object showed up on December 3rd of 2007, or that the author called it Phil. You probably need to know something about what's inside of it. Now, you could ask the author to generate all the metadata for you and give it to you separately, but most people aren't going to want to do that. And for a lot of stuff that you're collecting, it would make no sense to do that. Let's say this was an image that was coming in, and let's say you had 100 of them that you wanted to put in, or maybe it was even a stream of stuff. You're not going to want to go through every single image, I believe, and figure out what it is to say about it from a metadata perspective. And yet, when you go in to try and access it at a later time, you're going to need to know things that you didn't think about. I didn't think to mention that you were in that picture, and well, maybe you could be found because you're so distinctive that anybody can pick you out of any picture at a moment's notice, but most people can't, or can't be found that way. And so unless you've got something that knows how to do that in these proprietary data structures, you're in trouble. So that's one thing we can do. Second thing that we can do is map those things, if we know what kind of thing they are, into some standard form. I'll give you an example. I think what we now know as spreadsheets will have some kind of longevity going forward. I don't know exactly what form they'll take. They may be 3D spreadsheets, they may be in hyperspace, who knows what they'll look like. But let's say for the moment, there's a generic kind of an object called a matrix. That's what a spreadsheet is. It's got so many rows, so many columns, so many cells, and that's something we've actually been working on. Let's say we could describe that in some generic form. If you give me a spreadsheet, I don't know what's in the proprietary structure, but I know it's got m rows and n, you tell me, or I can figure out. It's got m rows and n columns, and I can figure out what's in every row and column. So my object says the ijth element is such and such. And maybe I store the original, and maybe I store the abstracted version. And then at a later point in time, 1,000 years from now, if I pull this out, let's assume the semantics are such that the word matrix means something. Yeah, I mean, it hasn't changed its nature. So they know this is something that's got rows and columns. They can pull it back out. They can then import it into any system of the future that's got all the bells and whistles. It knows about colorization and printers and screen formats and all the stuff that you need to manifest the data. But you're able to get it and import it. Now, you could argue that maybe 1,000 years from now, somebody will build the interfaces to import, Microsoft's spreadsheet or the VisiCalc spreadsheet. But I wouldn't bet on it. I don't even bet that they'll keep things in 10 years from 10 years ago, much less, for a millennia. But I think you can get into that intermediate stage and actually make things work.
This sounds to me like it's an area where lots and lots of research would be well worth the effort.
And I think that's exactly what's going to happen. We may play a part in helping to organize some of that. But just to show you how difficult a problem this is, what do you think could be easier to characterize than an image? I mean, all it is a set of pixels.
Yes, although as soon as those images are compressed in any way, suddenly you have a whole algorithm to worry about to undo that to generate the appropriate pixels.
I'm going to say that compression is not allowed. We have so much memory, you don't have to compress it. You're right, if you compress it, you got to understand how to uncompress it and the like. But let's just say you have an image, a certain number of pixels, and you'd think that interchangeability between any two parties would be identical. And yet I'm sure if you go to the camera industry today that they all have different ways of standardizing things. And the reason is that not only do they have different ways of characterizing the elements of their pixels, but they probably all embed metadata and what kind of camera it came from, and they have all this other stuff, and it's all in some probably proprietary data format unless they agree to share it all. So it's more than just more than just the images. I often think about what I was once calling knowledge attachments. If you got a map of something, it's one thing to have something that will enable you to understand just the map. But suppose somebody then annotates it to tell you what the street names are, the buildings, the legacy of the buildings, how much the building costs, where the sewage drains. I mean, you may not know how to process that image if you knew about processing maps, because you don't know how they coded it and what all the details are, and what you think are images or pixels turn out to be something different. So without knowing how it was all coded together, you're dead in the water. So I think keeping one's leg up on how that's going is going to be important. And I think the only way to do it, quite frankly, is to specify standards for people who write programs who know what their proprietary data structures are, not to disclose them, but to generate relevant metadata that might be of interest according to some external standards, so that the programs can generate it without necessarily disclosing proprietary data structures.
In some ways, this is reminiscent of what happened with the web, because the original HTML was being generated by hand, and then eventually that got a little tiresome, and people wrote programs that would allow you to do direct manipulation of the content, images, and text, and generated the HTML for you. Getting something to generate the appropriate metadata is probably part of the problem. I have to say, when I think about spreadsheets, that trying to retain their interpretability over long periods of time is really tough, because if you look at the content of any one of the matrix elements, it could have all kinds of references with identifiers in those references.
And it should.
Well, that's what gives spreadsheets their power. But when they start making references to other spreadsheets by file name or by URL or by some other thing,
Dead in the water.
Or at least you have a really tough transformation problem if you're trying to retain that over a long period of time.
Yeah, like 1,000 years from now. I mean.
So in some ways, there's a digital Tower of Babel facing us as we start accumulating more and more digital information if we don't start tackling these problems. So I'm glad that we had time to bring them up. Well, I think we should try to round this off with a couple of future-looking questions, if you have the energy to do that. Since you've had such a key role in the development of the internet, maybe you'd care to speculate about what its future is likely to be like. And there are any number of axes in which to answer that. One could be the technological one, another could be policy, another could be governance, and another could be applications, and you can probably think of others. But as you think a little bit about this thing that you were so central at creating, do you have any current sense of where you think it's likely to go and in what directions it's likely to evolve?
Seems to me you've been even more vocal than I have on this subject in different quarters, so I'm sure you've got your own views. But, I don't really know where to begin on that, because I could tell you what's obvious now. But remember I said leave a little room for serendipity? I mean, the things that are going to shape the internet in the future are the unknowns that just change the dynamics of everything in unpredictable ways. You know, I am sure the founding fathers must have debated what's this country going to look like, you know, in 1830 or in 1870, and you know, they would have had to throw up their hands, because how could they have predicted the Depression of 1930? How could they have predicted the Vietnam War? How could they have predicted what the world looks like right now? I mean, you build an organic system and let it go. The internet is really a dynamic organic system. I mean, I could tell you that wireless will become a more endemic part of the system in all ways. You know, we could even speculate about whether wires will go away or not. I don't think they will, by the way. Or maybe they will, because there'll be fibers somewhere or other. You know, we could speculate about how much bandwidth will show up. We could speculate about how much information is relevant to keep. We could speculate about, you know, will people ever throw anything away anymore? We could speculate about the liability of keeping all that information around. I mean, maybe, you know, it's worth spending a lot of time to get rid of stuff. Or maybe it's becomes mandatory to figure out, you know, what you need to get rid of and budget it. I mean, I was really surprised to see in the financial standards now they require that you put on balance sheets the cost of rectifying problems that they know about that you might have to deal with in the future, like asbestos removal from a building. It's no longer possible to ignore that. You now have to figure out what it will cost you to remedy that, put it on the balance sheet.
As a liability.
As a liability right now, even if you don't do anything about it for a long time, because ultimately when that building comes down, you're going to have to deal with it as a separate issue. You can't just demolish the building. So, you know, who knows? But I certainly think that the future of the internet is going to be tied to information access, information management, collaboration among individuals to a much greater extent than it is now. I think we'll see the World Wide Web as a first step in information access. There will be many other systems that get evolved as we go down the pike. And just like the ARPANET was not the first and only network that took over the world, the web's got a lot of worldwide penetration, and it's in its name as well. But eventually there'll be other good ideas that people have. We can't predict what they are, and they will embed themselves. I think the ability to access information of all kinds at any time is going to have profound implications that I wouldn't even want to speculate on right now, because if you can know whatever you want, whenever you want to, it can have the appearance of making you an awful lot more savvy about things than maybe you really are, but who knows what the effect of that is. I mean, you might as well ask, would this be a better planet if everybody were smarter? Or if everybody were dumber? Or if the span were bigger or smaller? And I don't think you can answer that, because everybody adapts. I remember once visiting my sister, whose husband was a doctor in public health service. They were in Cali, Colombia. And, you know, I'm used to living in a place where, you know, it might get down to minus 10 or 20 in the wintertime, and it could be 100 or even 110 in the summer, so there's a fairly big range. In Cali, Colombia, I think the low for the day was like 70.5 degrees when we were there, and the high for the day was maybe 72. So there maybe was a 1 or 2 degree differential. And people would come out in the morning with sweaters on, saying, and they'd take them off in the afternoon because they were all sweaty and hot, and then they put the sweaters back on again at night, because they adapted to the dynamic range that they saw. And I think it's very hard to, you know, predict exactly what kind of dynamics we'll have in different things going forward in the future. I think the one thing that's going to be with us from now on is the need for pervasive connectivity. And right now we see it mainly in an earthbound context. Some folks, yourself included, have been thinking about, you know, the planetary reaches. I'm not sure what an individual will need to do relative to, you know, planets like Jupiter or Pluto or whatever, but who knows? Who knows what businesses might develop about information access to things you would think have no value today, but that could develop as well. information you think is really important today may turn out to be of no value in the future. Things that you didn't think you could even know about turn out to be the most critical things in the future, and you can't live without them anymore. We may start to measure things that today get written off as unimportant because minor changes are indicative of major calamities down the road, and we know how to do those correlations. I'd love to be around to see how it all evolves, but I'm sure that what we will have is the need for this technical connectivity. We now know the power of the computing technology regime, but I don't know whether that's a passing fad and will be replaced by something else that's got those same kind of capabilities and more. Microfluidic computation systems, things that could be embedded and powered by chemical reactions in the body. I mean, who knows what the future really will hold, but whatever it is, I think the ability to link these kind of things together will be with us for a long time. So that to that extent, I think the internet legacy, regardless of what the protocols are, whether it's TCP IP or its next generation, or whether it's IP or its next generation, I think what we were able to demonstrate was the ability of things to interconnect on a global basis, maybe beyond. And I think it will be as important to the world as just sort of identifying for the first time the importance of transportational systems. And it doesn't matter whether it's your feet or a car or a train or a plane or whoever knows what comes next. If somebody generates an ESP system to move you from point A to point B, you'd say, well, that's just another example. And even though the technology may be pretty hard, so we don't know what it's going to look like, but I think there's something fundamental going on here, and I think it'll be with us for a long time. I was delighted to have been part of it. I was especially delighted to have worked with you on it, and in many ways even more so with Patrice, because we did it very intimately. But I think the world will look back and see this as one of the major contributions in history.
Thank you, Bob, for taking so much time. This is pretty special, I think, because it demonstrates, this long discussion demonstrates the breadth and depth of contributions that you've made personally. And so I'm glad to see that the Computer History Museum is recognizing that. I'm sure they'll take some small bits and pieces out of this many-hour discussion to share with the people who will celebrate with you at the museum event that recognizes your fellowship. I wish I could be there with you. My calendar isn't going to permit it, but I'll be certainly there in thought. And again, appreciate very much your time today. Thank you.
Thanks very much, Vint. Thanks very much for enabling all this.